Something strange is happening in the universe, something that defies expectations, something that shouldn't exist, and yet it does. When massive stars reach the end of their life cycle, they are supposed to explode in a fiery death, scattering their elements across the cosmos. That's what we've always believed. That's what we've been taught. But what if I told you that some stars don't explode? Instead, they just vanish. No supernova. No massive explosion. No trace. These are called failed supernovae, and they might be one of the greatest space mysteries we've ever encountered. We're used to things making sense. We think we know how stars live and die, but failed supernovae challenge that understanding. They suggest that some of the biggest stars in the universe, instead of going out with a bang, simply collapse in on themselves and disappear into the darkness. No explosion. No bright flash. Just a silent collapse into a black hole. And the strangest part? We have evidence that this is really happening. Think about what this means. A star, millions of times larger than Earth, burning for millions of years, should create one of the most energetic events in the universe when it dies. That's the way it works, right? But what if that explosion never comes? What if the star collapses so quickly, so efficiently, that all of its energy is swallowed up instantly? No fireworks, no spectacle, just a sudden disappearance. Scientists have actually observed stars that seem to blink out of existence without an explosion, and they're scrambling to figure out why. Failed supernovae change everything we thought we knew about stellar death. And if they really exist, they could mean that black holes form far more often than we expected. They could also mean that entire galaxies might have stars that died in silence, without us ever realizing it. But how is this possible? Why do some stars explode while others don't? And if stars can just disappear without a trace, could there be other cosmic mysteries that work the same way? Could there be entire celestial events happening right now, just out of our reach, that we'll never even notice? The idea of a failed supernova is terrifying in a way. A star, one of the brightest objects in the universe, can just vanish without a sound. No warning. No signal. It's as if it never existed at all. And the scariest part? We don't know how often this happens. We don't know how many stars have already died in silence. We don't know how many more will disappear before we even realize they were there. But let's break this down. What exactly is a failed supernova? To understand that, we need to take a closer look at what normally happens when a massive star dies. When a star reaches the end of its life, its core starts to run out of fuel. The star relies on nuclear fusion to keep itself stable, pushing outward with energy to counteract the immense force of gravity trying to collapse it. But when that fusion stops, gravity wins. The core collapses, and normally, this collapse triggers an explosion, a supernova. The outer layers of the star get blasted into space, while the core might collapse into a neutron star or, if the star is massive enough, a black hole. That's the standard model. That's what we expect. But failed supernovae suggest that, in some cases, the core collapse happens so quickly and so completely that the explosion never gets a chance to occur. Instead of a supernova, the star's core just keeps collapsing until it forms a black hole directly. There's no outward explosion, no ejected material, just a massive star suddenly disappearing from sight. And the evidence for this? It's already out there. Astronomers have identified stars that seem to be on the brink of explosion, huge, unstable, ready to die, only to suddenly vanish without a trace. One of the best-known examples happened in a galaxy 22 million light-years away. A massive star, about 25 times the mass of the Sun, was expected to explode. But instead, it just disappeared. No supernova. No explosion. Just gone. At first, scientists thought maybe the explosion was just hidden behind dust, or maybe it was too faint to see. But after years of searching, there was no evidence of a supernova at all. It was as if the star had simply collapsed into a black hole without making a sound. This was one of the first real hints that failed supernovae might be real. But why does this happen? Why do some stars explode while others don't? The answer isn't entirely clear, but scientists have some theories. One possibility is that, for certain massive stars, the collapse happens so quickly and so efficiently that all of the energy gets sucked into the forming black hole before an explosion can even occur. Normally, a supernova explosion happens because of neutrinos, tiny particles that carry away energy and help blow the outer layers of the star outward. But in a failed supernova, it's possible that those neutrinos get trapped inside the collapsing core, never escaping, never triggering an explosion. Another theory suggests that failed supernovae might happen in stars that have lost too much mass before dying. If a star sheds its outer layers over time, it might not have enough material left to create a visible explosion when it collapses. Instead of a dramatic supernova, the core just collapses quietly into a black hole, with no outward signs of its death. And then there's the most extreme idea, that some failed supernovae could be linked to the formation of the most massive black holes in the universe. If a star is big enough, its collapse might not just create a regular black hole, but something much larger, something that could eventually grow into a supermassive black hole, the kind that sits at the center of galaxies. If this is true, it could mean that failed supernovae play a huge role in shaping the cosmos. But the implications don't stop there. If failed supernovae are real, it means our current understanding of stellar evolution might be incomplete. It means that we might have been underestimating the number of black holes in the universe. It means that some galaxies might have entire populations of stars that have already collapsed, invisible and undetectable. And it raises an even bigger question: what else are we missing? If stars can die without an explosion, could there be other cosmic events happening right now, completely hidden from us? Could there be other processes at work in the universe that we've never even considered? The mystery of failed supernovae is just one piece of a much larger puzzle, one that challenges everything we thought we knew about the life and death of stars. But maybe the most haunting question of all is this: how many stars have already disappeared without us even noticing? And how many more will vanish before we ever get the answers we're looking for? The idea that stars can simply disappear without a trace challenges everything we thought we knew about the universe. Failed supernovae suggest that entire celestial bodies, massive stars that burn for millions of years, can just blink out of existence, leaving behind only darkness. This isn't just a minor detail in astrophysics. It could completely rewrite our understanding of how stars live and die. And if this is happening more often than we realize, it means the universe is hiding far more secrets than we ever imagined. But to fully grasp the scale of this mystery, we need to look deeper. How do we even know failed supernovae exist? After all, if something simply vanishes, how can we prove it was ever there to begin with? The answer lies in careful observation. Astronomers have been monitoring massive stars for decades, expecting them to eventually explode in brilliant supernovae. But in some cases, those stars have just disappeared instead. One of the most famous examples is a star in the galaxy NGC 6946, known as N6946bh1. This star, about 25 times the mass of the Sun, was bright and active, seemingly in its final stages of life. Scientists fully expected it to explode. But instead, in 2009, it just vanished. At first, astronomers thought the supernova might have been hidden behind dust. Maybe the explosion was too faint to see. But after years of searching, no sign of an explosion ever appeared. The star was simply gone. And when scientists looked closer, they realized something strange. There was a small source of infrared light in the same spot, exactly the kind of faint glow expected if the star had collapsed directly into a black hole. This was one of the first strong pieces of evidence for failed supernovae. It showed that massive stars really could collapse in on themselves without an explosion, leaving behind only a black hole. And if it happened once, it could have happened many times before, without us ever noticing. So how often do failed supernovae occur? That's the big question. Supernovae are already rare events. Only a few happen in a galaxy like the Milky Way every century. But if failed supernovae are common, it would mean that many stars we expect to explode are actually collapsing in silence instead. Some estimates suggest that up to 30% of massive stars might experience failed supernovae. If that's true, it means we've been drastically underestimating the number of black holes in the universe. Instead of forming only when a star explodes, black holes could be forming far more often, quietly and undetected. But how can we confirm this? How can we prove that failed supernovae are real if they leave behind almost no evidence? One method involves looking for disappearing stars. Scientists have started compiling lists of massive stars that should explode as supernovae, then checking back years later to see if they're still there. If some of them vanish without an explosion, that could be direct proof of failed supernovae in action. Another method involves studying the number of black holes in the universe. If there are far more black holes than expected, it would suggest that many of them formed without supernovae. By comparing theoretical models to real observations, scientists can estimate how many black holes were created through failed supernovae rather than explosions. And then there's the neutrino problem. Normally, supernovae release massive amounts of neutrinos, tiny, nearly massless particles that fly through space at incredible speeds. But if a star collapses straight into a black hole, those neutrinos might never escape. If we could detect sudden drops in neutrino emissions from dying stars, it might be another clue that failed supernovae are happening. But there's an even more mind-boggling possibility. What if some failed supernovae don't just form regular black holes, but something even stranger? Some scientists have speculated that under the right conditions, a collapsing star might create an entirely new type of object, something beyond our current understanding of physics. Could failed supernovae be connected to the mysterious dark matter that makes up most of the universe? Could they be forming exotic objects that we haven't even theorized yet? The truth is, we don't know. But the fact that stars can simply disappear without a trace suggests that there are forces at work in the universe that we still don't fully understand. Failed supernovae might just be the beginning of an even deeper mystery, one that could change everything we thought we knew about space. And if stars can vanish, what else might be slipping away unnoticed? Could entire galaxies be dying in silence? Could other cosmic structures be collapsing into the unknown without us even realizing? The universe is vast, and our knowledge is still so limited. But one thing is certain: if failed supernovae are real, then the universe is far more mysterious than we ever imagined. If failed supernovae are happening across the universe, then we need to ask an even bigger question: what does this mean for the future of space? For decades, scientists assumed that the deaths of massive stars were always marked by dramatic, violent explosions. Supernovae were thought to be an essential part of cosmic evolution, scattering heavy elements like iron, gold, and uranium across galaxies, seeding future generations of stars and planets. But if a significant number of stars are skipping this step entirely and collapsing into black holes instead, then the way we understand the life cycle of stars, and even the formation of the elements around us, might need to be reconsidered. Let's think about what this means in the long run. If failed supernovae are more common than expected, then fewer heavy elements are being spread across the universe. That could have serious consequences for the formation of planets, including those capable of supporting life. Supernovae play a critical role in enriching galaxies with the building blocks of life. Without them, the chemistry of space would be different, perhaps in ways we don't yet understand. Another consequence is the growing population of black holes. If failed supernovae are creating black holes at a higher rate than we expected, then the number of these invisible giants lurking in the darkness of space could be staggering. Right now, we estimate that the Milky Way alone contains millions of black holes, but if failed supernovae have been silently producing them for billions of years, that number could be even higher. This raises another mind-blowing possibility. What if failed supernovae are one of the reasons why rogue black holes exist? These are black holes drifting freely through space, untethered to any star system. Most black holes form at the centers of galaxies or in binary systems with other stars, but rogue black holes could be the remnants of failed supernovae, stars that collapsed quietly, without a supernova, and were then ejected from their original locations by gravitational interactions. And if failed supernovae are responsible for a vast number of black holes, could this explain certain gravitational anomalies we've observed? Scientists have long been puzzled by gravitational lensing effects, where light from distant galaxies bends in ways that suggest hidden, unseen mass. Dark matter is one explanation, but what if part of the answer lies in a vast, hidden population of black holes that formed silently through failed supernovae? Even more unsettling is what this could mean for the fate of our own galaxy. If failed supernovae are creating more black holes than we ever expected, then the cosmic balance of power could be shifting. Over time, as more massive stars collapse into black holes instead of exploding, the number of black holes in the universe could continue to rise, potentially leading to a future dominated by these mysterious objects. Could we be heading toward an era where black holes take over? Right now, most of the universe is still composed of regular matter, stars, planets, gas clouds, and galaxies. But black holes don't just disappear. They persist, lurking in the depths of space for billions of years, slowly merging and growing. If the process of failed supernovae has been silently creating them for eons, then black holes may be accumulating in ways we haven't yet fully realized. This also leads us to another deep and unsettling question. How many stars have we already lost to failed supernovae without even noticing? If we look back at old star catalogs from decades ago, could we find more stars that simply vanished? Are there regions of space where stars were expected to go supernova but instead fell silent? Some astronomers are already trying to answer this. By studying past observations and comparing them to the present, they're looking for signs of missing stars, objects that should still be visible but are now nowhere to be found. If more of these cases appear, then failed supernovae may be far more common than we ever thought. And if that's true, then one of the biggest mysteries of the universe is unfolding right before our eyes. Failed supernovae are showing us that space is not just full of dramatic explosions and dazzling cosmic fireworks. Sometimes, the most important things happen in silence. If failed supernovae are a common phenomenon, it would mean that for billions of years, the universe has been quietly forming black holes at a rate far greater than we ever suspected. This realization forces us to confront some unsettling truths about the nature of space and time. For decades, we believed that the deaths of massive stars were always marked by cataclysmic explosions, events so powerful that they could be detected from millions of light years away. These explosions, in turn, played a crucial role in shaping the chemical composition of galaxies, enriching them with the elements necessary for the formation of planets, life, and even the very atoms that make up our own bodies. But if a significant percentage of these stars are instead collapsing into black holes without producing a supernova, then much of the cosmic history we have built our understanding upon may need to be reconsidered. The absence of a supernova means that the process of dispersing heavy elements into space is not occurring in the way we thought. This could have vast implications, not only for the formation of new stars and planets, but for the entire evolutionary trajectory of the universe itself. The consequences of failed supernovae extend far beyond just the chemical composition of galaxies. If these silent collapses are happening regularly, they could be responsible for a vast and largely undetected population of black holes. Traditional models suggest that black holes typically form either through the explosive deaths of supermassive stars or through the slow accumulation of matter in dense stellar remnants. However, failed supernovae introduce an entirely new pathway, one in which black holes form not in dramatic, observable events but in complete darkness, slipping into existence without leaving any obvious clues behind. This raises the question, how many black holes have already formed in this way? If we assume that failed supernovae occur in roughly 10 to 30% of massive stars, then the number of black holes in the universe could be exponentially higher than we currently estimate. The Milky Way alone, already believed to contain millions of black holes, may in fact be harboring tens of millions or even more. If these silent collapses are more common than expected, then the number of rogue black holes roaming the universe could be staggering. Rogue black holes, those that wander freely through space, untethered to any specific star system, pose a unique challenge for astronomers. Because black holes do not emit light, they can only be detected through their gravitational influence on surrounding matter. This makes rogue black holes particularly difficult to find, as they lack the accretion disks and energetic emissions that typically make black holes visible. However, failed supernovae may be directly responsible for producing a significant number of these hidden objects. When a massive star collapses into a black hole without an explosion, it can sometimes result in a kick, where the newly formed black hole is ejected from its original position due to an asymmetry in the collapse. If this happens frequently, it could mean that rogue black holes are drifting through the interstellar void in far greater numbers than we have ever anticipated. The presence of these undetected black holes could help explain some of the most perplexing gravitational anomalies in the universe. For years, astronomers have observed mysterious gravitational lensing effects, instances where the light from distant stars and galaxies bends in ways that suggest the presence of unseen mass. While dark matter is often cited as the leading explanation for these effects, another possibility is that a significant portion of this unseen mass could be composed of rogue black holes formed through failed supernovae. If millions or even billions of these objects are scattered throughout the cosmos, their collective gravitational influence could be warping the fabric of spacetime in ways we have yet to fully comprehend. Another profound implication of failed supernovae is their potential role in shaping the long-term evolution of galaxies. Black holes exert a powerful gravitational pull on their surroundings, influencing the motion of stars, gas clouds, and even entire star clusters. If failed supernovae have been quietly adding to the population of black holes for billions of years, then the distribution of mass within galaxies may be significantly different from what we have traditionally assumed. Over time, as more stars collapse silently into black holes, the overall mass balance of galaxies could shift, leading to changes in their structure, rotation, and long-term stability. This could mean that some of the unexplained features we observe in certain galaxies, such as unusually high rotation speeds or unexpected gravitational interactions, might be the result of hidden black hole populations formed through failed supernovae. But perhaps the most mind-bending possibility of all is the idea that some failed supernovae might not just form standard black holes but could instead give rise to entirely new and exotic objects. While traditional physics predicts that a collapsing star should form either a neutron star or a black hole, some theoretical models suggest that under extreme conditions, other possibilities might emerge. One such possibility is the formation of an object known as a quark star, a hypothetical state of matter in which the fundamental building blocks of atoms, quarks, are compressed into an ultra-dense configuration. If quark stars exist, they could represent an entirely new class of celestial bodies, one that has remained undetected because we have not yet known where to look. Even more speculative is the idea that failed supernovae could be connected to the enigmatic nature of dark matter. Dark matter is one of the greatest mysteries in modern physics, accounting for roughly 85% of the total mass of the universe, yet remaining entirely invisible and undetectable through conventional means. While numerous theories have been proposed to explain dark matter, one possibility is that it could be composed of primordial black holes that formed not from dying stars but from fluctuations in the density of the early universe. If failed supernovae are far more common than we expect, they might be contributing to the dark matter mystery in ways we do not yet understand. It is possible that many of the black holes formed through failed supernovae are so small or so widely distributed that they have effectively blended into the cosmic background, influencing the evolution of galaxies without ever being directly observed. And then there is the question of whether failed supernovae might be occurring even in our own cosmic neighborhood. The Milky Way is home to thousands of massive stars that are expected to end their lives in spectacular explosions. But what if some of them simply disappear instead? Are there stars that were visible just a few decades ago that are now gone without a trace? Some astronomers are actively investigating this by comparing historical star catalogs to modern observations, searching for evidence of missing stars. If they find more cases like N6946BH1, the star that vanished in 2009 without a supernova, then we may be forced to confront the reality that failed supernovae are not just a rare anomaly, but a fundamental aspect of stellar evolution that has been happening right under our noses. What makes failed supernovae such a compelling mystery is that they challenge our very perception of how the universe works. We are conditioned to think of cosmic events as grand and dramatic, supernovae lighting up the night sky, black holes consuming everything in their path, galaxies colliding in spectacular displays of energy. But failed supernovae remind us that sometimes, the most profound changes in the universe happen in absolute silence. A star that shone for millions of years can simply vanish, leaving behind no explosion, no shockwave, no visible trace of its passing. It is a chilling thought, one that forces us to acknowledge just how little we truly know about the hidden mechanics of the cosmos. And if failed supernovae are only the beginning, what other invisible processes might be shaping the fate of the universe? Could entire galaxies be disappearing without our knowledge? Are there forces at work that we have yet to even conceive of? The more we learn about failed supernovae, the more it becomes clear that space is not just a realm of spectacular explosions and dazzling lights. It is also a place of silent collapses, unseen transformations, and cosmic secrets waiting to be uncovered. If failed supernovae are more common than we ever imagined, then the very nature of the cosmos is far more mysterious than we have previously believed. Imagine how many stars have collapsed into black holes without a trace, events that left no lingering supernova, no brilliant explosion, no outward sign that anything had changed. These silent collapses could mean that black holes are forming all around us, all the time, without us even realizing it. The universe might not be a place of constant violent endings, as we have assumed, but instead a realm of quiet disappearances, where some of the largest and most powerful objects in existence simply slip into darkness without fanfare. This forces us to ask an unsettling question. If entire stars can vanish without us noticing, what else could be happening right under our noses? One of the strangest aspects of failed supernovae is that they break our expectations of how massive stars should behave at the end of their lives. For years, astrophysicists have operated under the assumption that when a massive star reaches the end of its fuel supply, it must explode. The star's outer layers should collapse inward due to gravity, rebounding off the dense core and generating an immense shockwave that tears the star apart. This explosion, what we call a supernova, is supposed to be one of the brightest and most powerful events in the universe. But failed supernovae suggest that this process does not always happen. Instead of a dramatic explosion, the star simply collapses inward, forming a black hole instantly, without ejecting any material into space. But why? What determines whether a star will explode or simply disappear? One leading theory suggests that the answer lies in the star's core. When a star reaches the end of its life, the iron core must reach a critical mass before it can trigger a supernova. If the core does not reach this critical point, it may not generate enough pressure to produce the expected explosion. Instead, the collapse happens so quickly and so completely that the black hole forms in an instant, pulling in all surrounding material without releasing any visible light. In other words, these failed supernovae may not be failures at all, but rather an alternative, hidden pathway by which stars transform into black holes. But this idea raises an even more puzzling question. Why do some stars explode while others collapse silently? The answer may lie in something called the neutrino mechanism. During a typical supernova, an enormous number of neutrinos, tiny, nearly massless particles, are released in the collapse. These neutrinos carry away vast amounts of energy and help drive the outward explosion of the star's outer layers. But if a star does not produce enough neutrinos, or if the neutrinos fail to transfer their energy effectively, the explosion may never happen. Instead, all the material continues collapsing inward, leaving behind only a black hole. This suggests that failed supernovae are not simply a rare fluke but may actually be a fundamental outcome of stellar evolution under specific conditions. If neutrino interactions are slightly weaker than expected, or if certain elements in the star's core change the way neutrinos behave, then a supernova might fail to ignite, leading to a silent collapse instead. If this is true, then failed supernovae might also be connected to some of the most elusive particles in the universe, dark matter particles. Dark matter makes up most of the mass in the universe, yet we cannot see or detect it directly. One possibility is that certain types of dark matter interact with the collapsing core of a star in a way that disrupts the neutrino mechanism, preventing the explosion from occurring. If dark matter particles absorb or scatter neutrinos before they can do their job, then the explosion may fizzle out before it even begins. This would mean that failed supernovae could serve as indirect evidence of dark matter interactions, helping us unlock one of the biggest mysteries in modern physics. But let's take this idea even further. If dark matter is influencing the fate of massive stars, then it could also be shaping the distribution of black holes throughout the universe. If failed supernovae are happening more frequently in regions with high concentrations of dark matter, then these areas could contain far more black holes than we currently estimate. This might help explain certain gravitational anomalies observed in galaxies, where the motion of stars suggests the presence of hidden mass. If this mass is not entirely composed of dark matter, then it might instead include vast numbers of black holes formed through failed supernovae. These invisible black holes could be lurking everywhere, influencing the structure of galaxies in ways we have yet to fully understand. But there is another possibility, one that is even more unsettling. What if failed supernovae are not just forming black holes, but something even stranger? Some scientists have speculated that under extreme conditions, a collapsing star might not become a traditional black hole but could instead transform into an object known as a gravistar. A gravistar is a hypothetical object that exists on the edge of physics as we know it. Instead of forming a singularity, an infinitely dense point like a black hole, a gravistar would contain an exotic form of matter that prevents complete collapse. This would create a strange bubble-like structure, where the extreme gravitational pull is balanced by an unknown internal force. If gravistars exist, they could be completely invisible from the outside, much like black holes, but they would lack the event horizon that makes black holes so mysterious. This means that if failed supernovae sometimes create gravistars instead of black holes, then we may have been mistaking these objects for black holes all along. And if failed supernovae are forming these bizarre objects, then what else might they be creating? Could some collapsing stars be forming wormholes instead? A wormhole is a theoretical tunnel through space-time that could allow for faster-than-light travel between distant points in the universe. While no evidence of wormholes has ever been observed, some theories suggest that under the right conditions, the collapse of a massive star could create a wormhole instead of a black hole. If failed supernovae are more common than we thought, then it is possible that the universe is littered with these hidden gateways, portals to places unknown, waiting to be discovered. If all of this is true, then the silent deaths of stars could be one of the most important and overlooked phenomena in the cosmos. They could be quietly reshaping the universe, forming unseen black holes, hidden wormholes, exotic gravistars, and even influencing the structure of galaxies themselves. And the most chilling thought of all? We may never actually see one happen. Failed supernovae are, by their very nature, invisible events. They leave no explosion, no bright flare, no telltale signature that something has changed. The only clue is a missing star, an object that once burned brightly in the sky, only to suddenly vanish without a trace. And if this has been happening throughout cosmic history, then how many stars have already disappeared without us noticing? How many black holes have formed in silence, waiting in the darkness, hidden from view? The more we learn about failed supernovae, the more it becomes clear that the universe is far more mysterious than we ever imagined. There are forces at work that we are only beginning to comprehend, processes that defy our expectations, and cosmic disappearances that may hold the key to some of the greatest unsolved questions in astrophysics. But perhaps the most unsettling question of all is this: if we cannot see these events happening, then what else might be occurring in the universe, right now, beyond the reach of our instruments, and beyond the limits of our understanding? Could failed supernovae be just one of many invisible cosmic mysteries waiting to be uncovered? What else is hiding in the vast, silent darkness of space, shaping the universe in ways we have yet to perceive? If failed supernovae are happening all around us, silently forming black holes, what does that mean for our understanding of the universe? Think about it. For centuries, we believed that massive stars always end in a spectacular explosion, one that spreads heavy elements into space, seeds new stars, and even influences the chemical makeup of planets. But what if we were wrong? What if many of those stars don't explode at all? What if they simply collapse, leaving behind nothing but an invisible black hole, changing the cosmos in ways we never anticipated? This possibility forces us to rethink not only the life cycle of stars but also the very fabric of our universe. If failed supernovae are more common than we expected, then the number of black holes in the universe could be significantly higher than we thought. This would change our models of galaxy formation, dark matter distribution, and even gravitational wave events. Instead of a universe filled with the remnants of supernova explosions, we may be living in a cosmos quietly littered with hidden black holes, massive objects that exert their gravitational influence without ever revealing their origins. And here's where things get even stranger. If these failed supernovae are forming black holes without an explosion, how do we know they're even forming at all? How many black holes have appeared in the universe without us realizing it? We only detect black holes when they interact with nearby matter, when they pull in gas, dust, or even entire stars. But if a newly formed black hole exists in the vacuum of space, with nothing nearby to feed on, it would be completely undetectable. It wouldn't emit radiation. It wouldn't distort light in a way we could easily measure. It would simply exist, a silent, invisible predator lurking in the darkness. So how do we even confirm that failed supernovae happen? Scientists have turned to one of the most intriguing methods of detection, looking for stars that simply disappear. This may sound like science fiction, but astronomers have actually been doing just that, scanning the sky for bright stars that suddenly vanish without leaving behind any explosion or remnants. One of the most famous cases was a star named N6946bh1, located in the galaxy NGC 6946, about 22 million light-years away. This star, a massive red supergiant about 25 times the mass of the Sun, was expected to go supernova. But instead of exploding, it simply faded away. No bright flash. No supernova. Just nothing. At first, astronomers thought it might be a temporary dimming event, perhaps caused by dust or an unexpected change in the star's outer layers. But after years of observation, it became clear: the star had vanished. The best explanation? It collapsed directly into a black hole without an explosion, one of the first pieces of evidence for failed supernovae in action. And this discovery opened up a floodgate of new questions. If this happened once, how often does it happen? How many other massive stars have already disappeared without us noticing? This has led scientists to search for more disappearing stars, scanning distant galaxies for other instances of massive stars that wink out of existence. And while the search is ongoing, some researchers believe that failed supernovae might be much more common than we initially thought. If that's the case, then our estimates of black hole populations might be way off. There could be millions, perhaps billions, of black holes out there that we have never accounted for, quietly warping spacetime without ever revealing themselves. But the mystery goes even deeper. If failed supernovae are leaving behind black holes, then what kinds of black holes are they creating? Are these typical stellar mass black holes, only a few times the mass of our Sun? Or could some of them be forming something even stranger? One of the biggest unsolved questions in astrophysics is the origin of intermediate mass black holes that are larger than stellar mass black holes but smaller than the supermassive giants at the centers of galaxies. Could failed supernovae be responsible for their formation? Could they be the missing link in our understanding of black hole evolution? Some theories suggest that if a failed supernova happens in just the right conditions, it might create an unusually large black hole, one that continues to grow over time, consuming nearby material until it reaches an intermediate mass state. If this process is more common than we think, then failed supernovae might not just be forming typical black holes. They might be playing a crucial role in shaping the entire population of black holes across the universe. And then there's an even wilder possibility. What if some failed supernovae are forming primordial black holes? Primordial black holes are hypothetical black holes that could have formed in the early universe, long before stars and galaxies even existed. Some scientists believe that if these objects exist, they could account for some or all of the mysterious dark matter that makes up most of the universe's mass. But what if instead of being primordial, some of these black holes are actually forming right now, in real time, through failed supernovae? If failed supernovae are quietly creating vast numbers of black holes, then we might be living in a universe far stranger than we ever imagined, one where black holes are not rare endpoints of massive stars but rather a fundamental, invisible feature of cosmic evolution. These objects could be shaping the very structure of the cosmos, influencing the way galaxies form, merge, and evolve over billions of years. And the implications don't stop there. If failed supernovae are happening all around us, forming black holes at an unknown rate, then what does that mean for the future of our own galaxy? Could the Milky Way be filled with unseen black holes, drifting silently through space? Could some of these objects be much closer than we realize, hidden just beyond the reach of our telescopes? Could a failed supernova happen near us, creating a black hole that subtly alters the gravitational landscape of our galaxy? These questions push us toward the limits of what we know, and what we don't know, about the universe. And perhaps the most unsettling question of all is this: if failed supernovae are happening right now, how would we even know? Would we be able to detect the moment a massive star collapses into darkness? Or would it happen quietly, without warning, leaving us staring at an empty patch of sky where a star once shined? If failed supernovae are happening more frequently than we think, then it raises a mind-boggling question: how many black holes have already formed in total silence, without us ever realizing it? We've always assumed that most black holes come from supernova explosions, but if massive stars are skipping the explosion phase entirely, that means our galaxy, and the entire universe, could be littered with these invisible gravitational monsters. The scary part? Some of them might be closer than we ever imagined. The Milky Way alone is estimated to contain at least 100 million black holes, based on models that assume most massive stars explode as supernovae before collapsing into black holes. But if failed supernovae are a significant factor, this number could be much higher. There could be countless hidden black holes drifting through space, undetectable unless they interact with nearby matter. Some might even be passing through our cosmic neighborhood right now, their gravitational pull subtly influencing the orbits of stars and planets without us noticing. And here's where things get even more unsettling. What if one of these failed supernovae happened in our cosmic backyard? Massive stars exist in our galaxy, many of them relatively close to us in astronomical terms. If one of these stars were to undergo a failed supernova, it could create a black hole without any warning. No explosion, no bright flash, just a sudden, silent disappearance, leaving behind an invisible object warping space-time. The only way we'd know it was there would be if it started affecting the movement of nearby stars or accreting matter, producing detectable X-rays. But what if it didn't? What if it simply existed, undetectable and unseen? This leads to an even bigger question: how close could a black hole from a failed supernova get to our solar system before we noticed it? The truth is, we don't really know. A black hole drifting through interstellar space wouldn't necessarily emit any light or radiation. If it weren't actively pulling in matter, it would be almost impossible to detect. Some scientists believe there could be rogue black holes, remnants of failed supernovae, wandering through the galaxy, moving silently through the void. Some might be tens or hundreds of light years away. Others? Possibly even closer. This possibility has led astronomers to develop new ways to detect these hidden black holes. One method involves looking for gravitational microlensing events, moments when a black hole passes in front of a background star and bends its light due to its gravitational field. By studying how the light is distorted, scientists can estimate the black hole's mass and location. Using this method, astronomers recently discovered a black hole only about 5,000 light-years away, drifting through space at an incredible speed. Could it be the result of a failed supernova? We don't know for sure, but it raises the possibility that many more could be out there, hidden in the darkness. And then there's an even stranger idea, one that stretches the limits of our understanding of physics. If failed supernovae are forming black holes without any visible explosion, could there be cases where the collapse happens in an even more extreme way? Some scientists have speculated about the possibility of direct collapse black holes, objects that form instantly from collapsing gas clouds, without ever going through a supernova or even a traditional failed supernova process. If such objects exist, they could be the missing link in our understanding of how the first black holes formed in the early universe. These direct collapsed black holes might have been the seeds of the supermassive black holes we see at the centers of galaxies today. But what if they're still forming? What if some of the failed supernovae we detect are actually part of a much larger cosmic mechanism, one that creates black holes on a scale we've never imagined? Could failed supernovae be part of a process that is still actively shaping the universe? If that's the case, then we might be looking at black hole formation all wrong. Instead of thinking of supernovae as the primary way black holes form, we may need to consider failed supernovae and direct collapse as major contributors to the population of black holes in the universe. And if that's true, then we've only begun to scratch the surface of how many black holes are out there, and what role they play in the grand structure of the cosmos. This also brings us to another pressing question: how do failed supernovae fit into the broader picture of cosmic evolution? If massive stars are collapsing into black holes without explosions, then what does that mean for the distribution of heavy elements in the universe? Traditionally, supernovae are thought to be the primary way elements like iron, gold, and uranium are spread across space. These explosions blast out the materials that eventually form planets, moons, and even life itself. But if many of these stars are skipping the explosion phase, then what happens to all those elements? Some scientists suggest that failed supernovae might still eject some material before collapsing into black holes. This could happen through intense stellar winds in the final stages of a star's life, or through brief, weak eruptions that release some of the star's outer layers before the core collapses. But if this process isn't as efficient as a supernova explosion, then the heavy elements needed for rocky planets and life might be less abundant than we previously thought. Could this mean that certain regions of the universe are missing key elements because their massive stars underwent failed supernovae instead of explosive ones? Could this even influence the formation of habitable planets? And here's a truly wild thought: could failed supernovae be one of the reasons why intelligent life is so rare? If a large portion of the universe's heavy elements are locked away inside black holes instead of being spread through space, then the raw materials needed to build Earth-like planets, and eventually, civilizations, might be far less common than we expected. It's a sobering idea. The silent collapse of stars could be quietly limiting the number of planets that can sustain life. But there's another angle to consider, one that ties failed supernovae to one of the biggest cosmic mysteries of all: dark matter. We still don't know what dark matter is, but we do know that it makes up about 85% of the universe's total mass. Some researchers have proposed that a fraction of dark matter could actually be made up of black holes, particularly those that formed through failed supernovae. If that's true, then these silent, undetectable black holes might not just be cosmic oddities, they might be crucial to the structure of the entire universe. If a significant number of black holes are forming through failed supernovae, then they could be contributing to the unseen mass that holds galaxies together. Could this be the key to understanding dark matter? Could these hidden black holes be part of the missing mass that has puzzled astronomers for decades? And if that's the case, then what happens next? Are failed supernovae still creating dark matter like black holes today? Are we living in an era where new, undetectable black holes are constantly being born, shaping the universe in ways we can't yet perceive? And most importantly, how do we even begin to study something that, by definition, doesn't leave behind any visible clues? The answers to these questions could reshape our understanding of the universe. Failed supernovae may seem like a niche astrophysical phenomenon, but in reality, they might hold the key to some of the biggest cosmic mysteries we've ever encountered. They challenge everything we thought we knew about how stars die, how black holes form, and even how the universe itself is structured. And the scariest part? We might never see them coming. These silent, invisible events are happening right now, all across the universe, changing the cosmic landscape in ways we're only just beginning to grasp. The universe may be far darker, far stranger, and far more mysterious than we ever imagined. If failed supernovae are more common than we previously thought, then we have to reconsider our entire picture of stellar death and black hole formation. But there's another angle to this, one that ventures into the truly strange and unsettling. What if some failed supernovae don't just lead to black holes? What if, under extreme conditions, they create something even more bizarre, something we don't even have the words to fully describe yet? Some astrophysicists have speculated about the possibility of exotic remnants forming from these silent collapses. When a massive star undergoes a failed supernova, its core doesn't explode outward, it implodes. Theoretically, if enough matter is compacted into a small enough space, it forms a black hole. But what if, in rare cases, something else happens? There have been hypotheses about the existence of quark stars, or preon stars, which could be an intermediate step between neutron stars and black holes. Normally, when a star collapses, its core is crushed into an incredibly dense state, first into a neutron star, where protons and electrons merge to form neutrons. But if the pressure is even greater, the neutrons themselves could break down into their fundamental components, quarks. This would create an object so dense that it would behave almost like a black hole, but without an event horizon. If quark stars exist, they would be incredibly difficult to detect. They might appear as faint, ultra-dense remnants that give off weak radiation before eventually collapsing into black holes. Some researchers even suggest that certain black hole candidates we've identified might not actually be black holes at all, but rather exotic objects left behind by failed supernovae. If that's the case, then the universe might contain strange, ghostly objects we haven't even begun to classify. But let's take this idea even further. What if, under even more extreme conditions, some failed supernovae create something beyond our current understanding of physics? There are theories that suggest that, in the ultra-dense cores of collapsing stars, entirely new states of matter could form, matter so compressed that it defies everything we know about particle physics. Some have even suggested that these collapses could momentarily create microscopic wormholes or other distortions in space-time itself. If that sounds like science fiction, remember that black holes themselves were once considered purely theoretical. For decades, they existed only in mathematical equations, with many scientists doubting they could actually form in reality. But now we know they do. So what if there are other strange consequences of stellar collapse that we just haven't observed yet? One of the strangest possibilities is that failed supernovae could, under certain conditions, create dark, black holes, objects that don't interact with normal matter or light in any detectable way. Unlike typical black holes, which can be observed through their effects on nearby stars and gas, these objects would be completely invisible, even indirectly. They wouldn't accrete matter, they wouldn't emit radiation, and they wouldn't produce gravitational waves strong enough to detect. They would simply exist, like silent voids in space, completely undetectable to us. And if such objects do exist, then our understanding of black holes, and even gravity itself, might need to be rewritten. Could these failed supernova remnants be connected to dark matter? Could they be part of a hidden structure that influences galaxies in ways we've never considered? Some scientists have even gone so far as to suggest that failed supernovae could be one of the main ways dark matter is produced. If a significant fraction of massive stars collapse directly into undetectable black holes, then we might already be living in a universe filled with invisible remnants of failed stars. This could explain why dark matter is so difficult to detect. It might not be made of unknown exotic particles, but instead, it could be made of something we already know exists. Collapsed stars that left behind nothing but their gravitational pull. And that raises an even bigger question. What if the physics of failed supernovae is tied to something even larger, something that governs the structure of the entire universe? Could these silent stellar collapses be a crucial, hidden mechanism in cosmic evolution, shaping galaxies and influencing the large-scale structure of the cosmos? We've always assumed that the most powerful forces in the universe are the ones we can see. The explosions of stars, the collisions of galaxies, the radiation pouring from quasars. But what if some of the most important forces shaping the universe are completely silent? What if the key to understanding dark matter, black holes, and the fate of the cosmos lies not in what explodes, but in what vanishes? If we ever want to truly understand the universe, we need to find a way to study what we cannot see. Failed supernovae might hold the answers to some of the biggest questions in astrophysics. They challenge our assumptions about how stars die, how black holes form, and even how the very fabric of space-time behaves under extreme conditions. They remind us that the universe is still full of mysteries, silent, invisible, and waiting to be uncovered. And perhaps, as we continue to look deeper into the cosmos, we'll finally find the answers we've been searching for. Or maybe, just maybe, we'll discover that the truth is even stranger than we ever imagined. If failed supernovae are more than just a rare cosmic accident, if they are, in fact, a fundamental part of how the universe works, then we have to consider the consequences. Every time a massive star reaches the end of its life, we assume one of two things will happen. It will explode as a supernova, leaving behind a neutron star or a black hole, or it will collapse entirely into a black hole with little visible energy release. But what if that's not the whole story? What if some failed supernovae lead to something even more exotic, objects that don't fit into any known category? Theoretical astrophysicists have long speculated that certain extreme conditions could give rise to hypothetical objects like gravastars or boson stars. These aren't science fiction concepts. They emerge naturally from the equations of general relativity and quantum physics. A gravistar, for instance, is a proposed alternative to a black hole. Instead of forming a singularity, where matter collapses into an infinitely small point, a gravistar would be a hollow shell of ultra-dense material, surrounded by a thin layer of exotic matter that resists further collapse. Unlike black holes, gravastars wouldn't have an event horizon, meaning, in theory, information wouldn't be lost when matter falls in. If failed supernovae sometimes create gravastars instead of black holes, it would change our entire understanding of how matter behaves under extreme gravity. Then there's the idea of boson stars. Unlike normal stars, which are made of ordinary matter, boson stars would be composed of hypothetical particles called bosons, particles that don't behave like the protons and neutrons we're familiar with. If such objects exist, they would be incredibly difficult to detect, because they wouldn't emit light the way normal stars do. Some scientists have even suggested that certain supermassive black hole candidates might actually be boson stars in disguise. Could failed supernovae be the birthplace of these exotic objects? If even a small percentage of failed supernovae creates something other than black holes, then our entire picture of stellar evolution needs to be updated. Right now, astronomers assume that when a massive star collapses directly into a black hole, all of its mass disappears behind an event horizon, never to be seen again. But if some of these collapses produce unusual remnants, whether gravastars, boson stars, or something else entirely, then those objects might still be influencing their surroundings in subtle ways we haven't detected yet. And this brings us to another crucial question. If failed supernovae are more common than we think, then how many of them have already happened without us noticing? We only recently began identifying these vanishing stars in distant galaxies, and our current observational techniques are still limited. If hundreds, thousands, or even millions of stars have undergone silent collapse throughout the universe's history, then we could be surrounded by the remnants of these events without realizing it. This could also have huge implications for dark matter research. If a significant portion of dark matter is actually made up of invisible stellar remnants, failed supernovae that collapsed into objects we can't easily detect, then we may have been looking in the wrong place for decades. Instead of searching for exotic particles, perhaps the solution to the dark matter mystery is hidden in plain sight: dead stars that never exploded. But here's where things get even stranger. Some researchers have speculated that certain failed supernovae might not collapse all the way into black holes, but instead could form ultra-dense, compact objects that behave in ways we don't yet understand. Could these objects warp space-time in ways that mimic dark matter? Could they be responsible for unexplained gravitational anomalies we've observed in galaxies? And what about the failed supernovae we haven't yet detected? Right now, our ability to track these events is limited by how far away they occur and how faint their signatures are. But as our observational tools improve, we might start finding more and more examples of stars that simply vanish without a trace. If that happens, we may have to rethink everything we thought we knew about the life and death of stars. There's also the question of what happens inside a failed supernova before the collapse is complete. Some simulations suggest that, in certain cases, the collapsing core could undergo brief, violent oscillations before finally disappearing. Could these oscillations generate tiny ripples in space-time, weak gravitational waves that are just below our current detection threshold? If so, then future gravitational wave observatories might be able to detect the death throes of failed supernovae, giving us a new way to study these events. And then there's the possibility, however remote, that some failed supernovae could produce wormholes. This idea is still highly speculative, but certain theories suggest that under the right conditions, the intense gravitational forces at the heart of a collapsing star could momentarily tear a hole in space-time, creating a tunnel between two distant points in the universe. If that's true, then every failed supernova could represent a hidden portal, opening for just a fraction of a second before sealing itself shut. Of course, this is all theoretical, for now. But the fact remains that failed supernovae are one of the most mysterious phenomena in astrophysics, and we're only beginning to uncover their secrets. Every time we find another example of a vanishing star, we're one step closer to understanding what's really happening out there in the depths of space. And maybe, just maybe, we'll discover that these silent deaths aren't just cosmic failures. Maybe they're part of a much larger, hidden process that shapes the evolution of the universe itself. If failed supernovae are more than just a rare quirk of stellar evolution, if they represent a hidden process shaping the universe, then we have to ask, what else have we been missing? How many of these silent collapses have already happened in our galaxy alone? And what secrets are hidden inside the darkness left behind? One of the biggest challenges in studying failed supernovae is that, by definition, they don't produce the bright, explosive signals that normally alert astronomers to a star's death. Instead of a spectacular explosion lighting up the cosmos, the process unfolds in near silence. A massive star, potentially dozens of times larger than the Sun, simply fades from view, vanishing as if it were never there. If you were watching such a star through a telescope, you wouldn't see a dramatic final act. You would just notice, one day, that the light had gone out. But while the star itself disappears, the effects of its collapse could still leave traces. One of the most promising ways to detect failed supernovae is by looking for bursts of neutrinos, tiny, almost massless particles that barely interact with normal matter. Neutrinos are produced in vast quantities during the core collapse of a massive star, whether or not it results in a supernova explosion. When a star collapses into a black hole, a flood of neutrinos should be released just before the event horizon forms, carrying away some of the energy from the dying core. In theory, we should be able to detect these neutrino bursts using specialized observatories like Super Kamiokande in Japan or IceCube in Antarctica. But there's a problem. Neutrinos are notoriously difficult to detect. They pass through entire planets as if they weren't even there, interacting so weakly with other matter that only a tiny fraction can ever be observed. Even if a failed supernova released a massive burst of neutrinos, it would be like trying to hear a whisper in a hurricane. That said, if we could improve our ability to detect these neutrino signals, we might be able to find failed supernovae much more easily. Some researchers have even suggested setting up an early warning system, where a sudden spike in neutrino detections could alert astronomers to a collapsing star in real time. This would allow telescopes to focus on the event immediately, capturing whatever faint signals remain before the star fully disappears. But what if failed supernovae produce other detectable effects, ones we haven't even considered yet? Some theories suggest that, in certain cases, the collapsing core might generate weak but measurable gravitational waves. These ripples in space-time, first predicted by Einstein, have already been detected from merging black holes and neutron stars. If failed supernovae also create gravitational waves, then future observatories, especially next-generation detectors like LISA, the Laser Interferometer Space Antenna, could open a whole new window into these mysterious events. And then there's the question of what happens after the collapse. When a massive star fails to explode and instead implodes directly into a black hole, what remains of its outer layers? Some simulations suggest that, in certain cases, a faint, short-lived burst of energy might still be released as the black hole forms. This could come in the form of a weak gamma-ray burst, a brief flash of X-rays, or even a shockwave that gently pushes surrounding gas outward without triggering a full explosion. If these subtle after-effects exist, they might explain some of the strange, dim transient events that astronomers have observed in recent years, events that don't quite match the profile of a normal supernova but also don't fully resemble a black hole formation. Could these be the dying echoes of failed supernovae, the last whispers of stars that never got their grand finale? This also raises another fascinating possibility. Do failed supernovae sometimes almost explode but don't quite make it? Imagine a scenario where a massive star begins the supernova process but stalls partway through. The core begins to collapse, neutrinos flood out, and the outer layers start to expand, but then, instead of fully detonating, the star's gravity pulls everything back inward. The explosion fizzles out before it can fully develop, and the star quietly collapses into a black hole instead. If this happens, then some of the so-called failed supernovae might actually be partial explosions, events that start like a supernova but end like a direct collapse. These half-finished explosions could leave behind strange remnants that don't fit into any known category, creating cosmic oddities we haven't yet classified. And what about stars that are right on the edge of the mass limit for core collapse? Some researchers believe that certain stars, instead of forming black holes or neutron stars, might collapse into ultra-dense, exotic objects that we've never observed before. Could some failed supernovae give rise to quark stars, objects even denser than neutron stars, made entirely of quarks? Or strange stars, which might be composed of exotic matter beyond anything in the standard model of physics? The idea of strange stars is particularly intriguing because it suggests that failed supernovae might not just produce black holes and neutron stars. They might create something entirely new. In these scenarios, the collapse of a massive star could push matter into states we've never seen before, forming objects that exist on the very edge of known physics. If such objects exist, they could be lurking undetected in our galaxy, disguised as ordinary neutron stars or hidden behind the darkness of space. And that brings us to one of the biggest mysteries of all: how many failed supernovae have already happened without us knowing? Right now, we can only detect these events in nearby galaxies, and even then, we've only identified a handful. But if failed supernovae are more common than we think, then there could be millions of them scattered across the cosmos, their remnants drifting unseen through the void. Some astronomers believe that, in the distant past, failed supernovae might have been even more common than they are today. Early in the universe's history, the first generations of stars were far more massive than most stars today. These ancient giants, known as population 3 stars, burned hotter, lived shorter lives, and likely collapsed in ways that were different from anything we see now. Some of these early stars may have undergone failed supernovae on a scale we can barely imagine, seeding the early universe with black holes before galaxies had even fully formed. If that's true, then failed supernovae might have played a crucial role in shaping the cosmos. The first supermassive black holes, those that now sit at the centers of galaxies, might have formed from the direct collapse of these primordial stars. If that's the case, then failed supernovae aren't just a cosmic curiosity. They're one of the fundamental building blocks of the universe as we know it. And yet, despite their importance, these events remain some of the most elusive phenomena in astrophysics. Every time we look deeper into the cosmos, we uncover more questions than answers. What happens inside a collapsing star in those final moments before it disappears? Are there failed supernovae out there that behave in ways we haven't even imagined? And could the secrets of these silent deaths hold the key to some of the universe's biggest mysteries, dark matter, black holes, and even the nature of space-time itself? The truth is, we're just beginning to scratch the surface of what failed supernovae can teach us. As our telescopes get more powerful and our ability to detect subtle cosmic signals improves, we may start uncovering more of these vanishing stars. And when we do, we might realize that the universe is even stranger and more mysterious than we ever imagined. The more we think about failed supernovae, the more we realize just how much of the universe remains unseen. For every supernova explosion we observe, how many stars have collapsed into black holes unnoticed? How many stellar deaths have gone completely undetected because they produced no light, no fireworks, just an invisible collapse into darkness? The truth is, we have barely begun to grasp the true scale of these silent disappearances. Failed supernovae challenge one of the most fundamental assumptions in astronomy, that we can understand the universe by observing its light. Traditional telescopes rely on electromagnetic radiation, visible light, radio waves, infrared, X-rays, gamma rays, to paint a picture of what's out there. But a failed supernova produces almost none of these signals. It's an event defined not by what it emits, but by what it doesn't emit. It's like trying to study an animal species that leaves no tracks, makes no sounds, and hides in the deepest shadows. That means we have to rethink how we search for these hidden events. We've already mentioned neutrinos and gravitational waves as possible clues, but there's another potential method, looking for the effects of these silent collapses on their surroundings. Even if a failed supernova doesn't explode, its gravity still influences nearby matter. If the star was in a binary system, orbiting another star, then its sudden collapse could disrupt the entire system. The companion star might be flung outward at high speed, or its orbit could suddenly change. Astronomers have already identified a few stars moving at extremely high velocities, so-called runaway stars, or hypervelocity stars, that might have been ejected when their companions collapsed into black holes. These stars are moving so fast that some of them are on trajectories that will eventually take them out of the Milky Way altogether. Could some of them be survivors of failed supernovae? If so, then tracking their movements could help us map out where and when these silent collapses occurred. Another approach is to study the interstellar gas and dust around regions where massive stars once existed. If a star undergoes a typical supernova, it blasts heavy elements into space, enriching the surrounding gas with iron, oxygen, and other materials that later form new stars and planets. But if a star collapses without exploding, then it doesn't release these elements in the same way. That means certain regions of space might show unexpected chemical signatures, areas where we would expect to see the remnants of a supernova but instead find an unusual scarcity of heavy elements. In fact, some astronomers believe that failed supernovae could be a missing piece in our understanding of galactic evolution. We know that galaxies are built from generations of stars being born, living, and dying. Each supernova spreads elements that contribute to the next generation of stars. But if a significant number of massive stars don't explode, then we have to rethink how this process works. Could failed supernovae be quietly locking away vast amounts of heavy elements inside black holes, preventing them from ever being recycled into new star systems? If so, then these silent collapses might actually play a major role in shaping the chemistry of the cosmos. And then there's the ultimate question: what happens to the matter that falls into these newly formed black holes? When a star collapses into a black hole, its core contracts to an incredibly small, infinitely dense point known as a singularity. But what actually happens inside that singularity? The laws of physics as we currently understand them break down in these extreme conditions, making it impossible to know for sure. Some physicists speculate that the matter might be compressed into an exotic state that we have no way of observing. Others suggest that black holes might not be singularities at all, but something stranger, perhaps wormholes leading to other parts of the universe, or even entirely new universes. If failed supernovae are creating new black holes all the time, then they might also be producing countless hidden doorways into the unknown. Could these collapses be linked to some of the deeper mysteries of the universe, dark matter, quantum gravity, or the true nature of space-time? Some radical theories propose that black holes might actually be dark matter, or at least a significant component of it. If failed supernovae are constantly producing black holes that go undetected, then we might have far more black holes in the universe than we ever realized. And if black holes are more common than we thought, then what does that mean for the fate of the universe? Some cosmologists believe that, in the far future, black holes will dominate the cosmos. Stars will burn out, galaxies will disperse, and all that remains will be black holes slowly evaporating over trillions of years through Hawking radiation. If that's the case, then failed supernovae aren't just a strange quirk of astrophysics. They're part of a process that will eventually reshape the entire universe. But before we get lost in the distant future, let's return to the present. Right now, the biggest challenge is simply identifying failed supernovae when they happen. One promising strategy is to look at long-term surveys of the night sky. Projects like the Large Synoptic Survey Telescope, LSST, which will capture detailed images of the sky over time, allowing us to track stars that mysteriously vanish. If we start seeing more cases of stars that should have exploded but didn't, we might finally begin to understand just how common these events really are. And when we do, we might find that failed supernovae aren't just rare exceptions. They could be a fundamental part of how the universe evolves. They could be shaping galaxies, creating black holes, and influencing cosmic structures on scales we've never imagined. We've spent centuries studying the light of the universe, but maybe some of its greatest mysteries lie in the things that disappear into the dark. If failed supernovae are more common than we currently believe, then we need to rethink everything we know about the life cycle of massive stars. Right now, most of our models assume that a star's final fate is either a brilliant supernova explosion or a quiet transformation into a white dwarf if it's not massive enough to collapse further. But if a significant percentage of massive stars are simply collapsing into black holes without an explosion, then our understanding of stellar evolution is missing a crucial piece. One of the biggest implications of failed supernovae is how they affect the overall structure of galaxies. Supernovae don't just create elements for new stars. They also push and stir up interstellar gas, influencing how and where new stars form. If fewer stars are exploding, then galaxies might not develop the way we expect. Could some galaxies be unusually quiet, lacking the normal turbulence we associate with stellar deaths? Could entire regions of space be shaped by the absence of these explosions rather than by their presence? Astronomers have already identified some puzzling cases where galaxies don't seem to behave the way our models predict. Some dwarf galaxies, for example, have far fewer heavy elements than expected, suggesting that their stars didn't enrich their surroundings the way they should have. Could these galaxies be filled with failed supernovae? Instead of blasting their elements into space, these stars might have collapsed into black holes, locking away their materials forever. And then there's the question of how failed supernovae relate to the overall black hole population. If a failed supernova is the birth of a black hole, then every one of these silent collapses means another black hole being added to the universe. This raises a serious question: just how many black holes are out there? We already know about some black holes from gravitational wave detections and X-ray observations, but these are just the ones that are actively interacting with their surroundings. If most black holes come from failed supernovae, then we might be missing an enormous hidden population of completely silent black holes drifting through space. These black holes could be everywhere, lurking unseen in the darkness, affecting their environments only through gravity. Some might be passing through interstellar space, undetectable except for their gravitational pull on nearby stars. Others might be part of binary systems, quietly siphoning material from a companion star but without emitting enough radiation for us to easily detect them. There could even be black holes wandering through our own galaxy, invisible except for the way they bend the light of background stars, a phenomenon known as gravitational microlensing. Gravitational microlensing is one of the only ways we can detect these hidden black holes. When a black hole passes in front of a distant star, its gravity can act like a lens, briefly magnifying the star's light in a way that reveals the presence of an otherwise invisible object. Some of the microlensing events we've observed suggest the presence of rogue black holes, objects with no visible counterpart that might be the remnants of failed supernovae. If we start finding more of these dark objects, we might finally get a sense of just how many stars have died in silence. Another key question is whether all massive stars are equally likely to experience failed supernovae, or if only certain types of stars are at risk. Some studies suggest that stars between 17 and 25 times the mass of the Sun are the most likely candidates, while more massive stars might explode more reliably. If that's true, then we might need to revisit our entire classification of supernova progenitors. We might find that a huge percentage of the stars we thought were going to explode are actually disappearing into black holes without a trace. This has major implications for our understanding of the early universe as well. The first generations of stars, known as population 3 stars, were much more massive than today's stars, and their deaths played a crucial role in shaping the formation of galaxies. If some of these early giants collapsed without an explosion, then the chemistry of the early universe might have evolved differently than we thought. Instead of enriching their surroundings with heavy elements, these stars might have left behind vast regions of space filled with dark, unseen black holes. Failed supernovae might also be connected to some of the biggest cosmic mysteries, including dark matter. Dark matter makes up most of the mass in the universe, but we still don't know what it is. Some scientists have proposed that dark matter could be made up of primordial black holes that formed in the early universe rather than from collapsing stars. But what if a portion of dark matter is actually made up of failed supernova remnants? If these events are more common than we realize, then the number of black holes in the universe could be high enough to account for at least some of the missing mass. Another possibility is that failed supernovae might be contributing to another unexplained phenomenon, fast radio bursts, FRBs. FRBs are incredibly powerful, millisecond-long bursts of radio waves that come from deep space. We still don't know what causes them, but some theories suggest they could be linked to the formation of black holes. If failed supernovae sometimes produce a brief but intense burst of energy before going dark, then they might be one of the hidden sources of these mysterious signals. But perhaps the most intriguing possibility is that failed supernovae could be a doorway to entirely new physics. Right now, our understanding of black holes is based on Einstein's theory of general relativity, which predicts that once matter falls inside a black hole, it's lost forever. But quantum mechanics suggests that information can't be truly destroyed. This contradiction is known as the black hole information paradox, and it's one of the biggest unsolved problems in physics. Failed supernovae might provide a natural laboratory for studying this paradox. If we can find a way to observe these collapses in real time, perhaps through neutrinos, gravitational waves, or other exotic signals, we might gain new insights into what happens at the very moment a black hole forms. Some theories suggest that, instead of a singularity, the core of a collapsing star might form a strange new state of matter, something beyond our current understanding of physics. Some scientists have even speculated that failed supernovae could produce exotic objects called gravastars, or fuzzballs, instead of traditional black holes. These hypothetical objects would look like black holes from the outside but would behave differently on a quantum level, potentially solving the information paradox in ways we haven't yet imagined. If we can study failed supernovae more closely, we might find evidence that challenges everything we thought we knew about space, time, and gravity. Ultimately, failed supernovae are a reminder that the universe is still full of secrets. We used to think that every massive star ended its life in a spectacular explosion, but now we know that some stars simply vanish. What else might be disappearing right before our eyes? What other cosmic events might be happening in the dark, beyond the reach of our telescopes? The answers to these questions could reshape our entire understanding of the cosmos, and failed supernovae might be the key to unlocking some of the universe's deepest mysteries. The idea that some stars simply vanish without an explosion challenges one of the most fundamental aspects of astrophysics. If we assume that a large number of massive stars bypass the supernova stage entirely, then we have to ask, how many stars in the universe have already disappeared this way? And more importantly, how can we detect something that leaves behind no obvious trace? The answer might lie in some of the most cutting-edge techniques available today, including gravitational wave astronomy, long-term stellar monitoring, and high-energy neutrino observations. One of the most promising ways to confirm failed supernovae is by tracking massive stars in nearby galaxies and seeing if any of them disappear. Traditional optical telescopes are not always ideal for this, as the regions where massive stars reside tend to be filled with dust and other material that can obscure our view. However, infrared telescopes, like the James Webb Space Telescope, can see through this dust and allow us to monitor individual stars over time. If a massive star vanishes without a trace, it could be a strong candidate for a failed supernova. But how do we know if a star has actually collapsed into a black hole instead of simply dimming or being obscured by dust? This is where gravitational waves might come in. When a black hole forms, it could produce a unique gravitational wave signal, especially if the collapse is asymmetric or if material briefly forms an accretion disk before falling in. While these signals would be much weaker than those produced by colliding black holes or neutron stars, future generations of gravitational wave detectors, such as the Einstein telescope or the Laser Interferometer Space Antenna, LISA, might be able to pick them up. Another possible signature of failed supernovae is a sudden burst of neutrinos. During a normal supernova explosion, a massive number of neutrinos are released as the core collapses, carrying away most of the energy. In the case of a failed supernova, a similar but fainter neutrino burst might still occur, even though the explosion itself never happens. If we can detect these neutrinos using observatories like IceCube in Antarctica or Hypercameo Candy in Japan, we might be able to confirm that a star has collapsed into a black hole without an explosion. There's also the possibility that failed supernovae leave behind some residual electromagnetic signals, though not nearly as bright as a typical supernova. Some researchers have proposed that, in certain cases, the collapsing star might briefly form a disk of material around the newly created black hole, producing a short-lived flare of X-rays or radio waves before fading into darkness. If this happens, telescopes like NASA's Chandra X-ray Observatory or the upcoming Square Kilometre Array (SKA) might be able to pick up these faint, dying signals. But perhaps the most unsettling question is what happens to all the failed supernovae that have already occurred throughout cosmic history. If these silent collapses are common, then our universe could be littered with far more black holes than we currently estimate. Some of these black holes might be actively pulling in matter, forming bright accretion disks and producing X-rays, but many more could be completely dormant, drifting invisibly through space. These rogue black holes could be a major hazard. If a black hole formed from a failed supernova is moving through space without any surrounding material to illuminate it, it would be nearly impossible to detect. Such objects could theoretically pass through our own solar system without us knowing, unless they interacted with a planet or disrupted the orbits of nearby stars. While the chances of a rogue black hole passing close to Earth are extremely low, the possibility adds another layer of mystery to the study of failed supernovae. There's also the question of how failed supernovae might influence the overall evolution of galaxies. We usually think of supernovae as playing a key role in galactic ecology, spreading heavy elements and triggering new waves of star formation. If a significant number of stars are instead collapsing quietly into black holes, then galaxies might develop in ways we don't yet understand. Could some galaxies be missing the heavy elements that should have been produced by supernovae? Could certain types of galaxies have vastly different black hole populations than others? The implications extend beyond individual galaxies. If failed supernovae have been happening throughout the history of the universe, then they could have played a role in shaping cosmic structure on a much larger scale. We know that black holes can merge over time, forming larger and larger objects. Could some of the supermassive black holes at the centers of galaxies have been built up from generations of failed supernovae? If so, then these quiet collapses might have been a hidden driving force behind some of the universe's largest and most extreme objects. Even more speculative is the idea that failed supernovae might help explain some of the biggest mysteries in modern physics. One of these is the nature of dark matter, the invisible substance that makes up most of the universe's mass. Some scientists have suggested that a portion of dark matter might be composed of primordial black holes, objects that formed in the early universe before stars even existed. But if failed supernovae are more common than we think, then perhaps some of the dark, unseen mass in the universe is actually made up of these hidden black holes. Then there's the question of whether failed supernovae could be connected to exotic forms of matter or new physics. When a star collapses into a black hole, does all of its matter truly vanish behind the event horizon? Or could there be new states of matter that form in the extreme conditions of a failed supernova? Some physicists have speculated that, under the right conditions, collapsing stars might give rise to objects like quark stars, boson stars, or other unknown forms of compact matter. If any of these objects exist, they could completely change our understanding of what happens when a star dies. The mystery of failed supernovae is not just about understanding how stars live and die, it's about uncovering some of the deepest secrets of the universe itself. We've always assumed that the most dramatic cosmic events are the ones that shape the universe, but what if the quiet, undetectable ones are just as important? What if, hidden in the darkness between the stars, there are countless black holes silently shaping the evolution of galaxies, the structure of space, and even the fundamental laws of physics? The search for failed supernovae is just beginning, and as our technology improves, we might start to uncover more and more of these hidden events. Future telescopes, gravitational wave detectors, and neutrino observatories could finally provide the evidence we need to confirm their existence. But for now, we're left with one of the most unsettling questions in astronomy. How many stars have died without a sound, and what else might be vanishing from the universe without us ever noticing? The deeper we dive into the mystery of failed supernovae, the more unsettling it becomes. Imagine looking up at the night sky, knowing that some of the bright stars we see might have already vanished, completely gone, collapsed into black holes without a single visible trace. We assume that stars live out their final moments in brilliant explosions, lighting up the cosmos and leaving behind spectacular remnants. But what if many of them don't? What if entire stellar populations are simply fading into the abyss, leaving nothing behind but invisible gravitational monsters? To truly grasp how many failed supernovae might be out there, we need to understand the life cycle of massive stars in more detail. Traditionally, when a star reaches the end of its nuclear fuel supply, its core collapses under the immense weight of its outer layers. This collapse leads to either a neutron star or a black hole, with an explosion, what we call a supernova, accompanying the process. But in certain cases, the star doesn't explode. Instead, the core collapse occurs so smoothly that almost all of the star's mass falls straight in, forming a black hole in an instant. The only sign of the event might be a brief pulse of neutrinos, fleeting, nearly undetectable particles that barely interact with normal matter. This raises a disturbing question: how many massive stars are vanishing this way without us knowing? The best way to estimate this is by looking at the number of massive stars we expect to see versus the number of supernovae we actually observe. Based on our current models, there should be more supernovae happening than we actually detect. This suggests that some stars must be undergoing core collapse in a way that doesn't produce an explosion, meaning failed supernovae could be more common than we ever imagined. To make things even more mysterious, some researchers suspect that failed supernovae could be responsible for some of the missing black hole populations we expect to find. We know that stellar mass black holes, those formed from dying stars, should exist in large numbers, but so far, we've only detected a fraction of the black holes that should be out there. Where are they? Could it be that a large portion of them formed quietly, without any supernova to announce their arrival? If this is true, then space is littered with hidden black holes, drifting unseen through the universe. The idea of silent black holes lurking in the darkness is unsettling enough, but what if some of these failed supernovae do leave behind clues? One intriguing possibility is that, in certain cases, a star's outer layers might take longer to fall in than its core. This could lead to a brief but powerful burst of light, what astronomers call a shock breakout, before the star disappears completely. Detecting these shock breakouts would be incredibly difficult, but they could provide one of the few observable signatures of a failed supernova. Another potential clue comes from what's known as the red supergiant problem. Red supergiants are massive, dying stars that should frequently explode as supernovae. However, when astronomers look at the data, they find that fewer red supergiants are going supernova than expected. This suggests that some of them might not be exploding at all. They might be collapsing straight into black holes instead. If this is happening, it could explain why we don't see as many supernovae from these stars as we predict. The implications of this are massive. If many stars are collapsing into black holes without exploding, then black hole formation is happening more often than we realized. This could mean that black holes play an even larger role in the universe than we currently think. It could also mean that certain galaxies have been shaped by silent black holes merging together, rather than by the explosive deaths of stars. And then there's the question of what happens to a black hole formed from a failed supernova. If a massive star collapses without exploding, the black hole it forms could be moving through space at the same velocity the star had before it collapsed. This means that rogue black holes not tied to any particular star system, could be much more common than we previously assumed. These invisible objects could be drifting through interstellar space, occasionally swallowing up gas, planets, or even entire stars without anyone noticing. This also raises the possibility that failed supernovae could contribute to the growth of supermassive black holes, the enormous black holes that sit at the centers of galaxies. One of the biggest mysteries in astrophysics is how these black holes grow so large so quickly. If failed supernovae are producing more black holes than we thought, then these silent collapses could be feeding the growth of supermassive black holes across the universe. But perhaps the most mind-bending aspect of failed supernovae is what they tell us about the nature of reality itself. When a black hole forms, it marks a point of no return, an event horizon beyond which nothing can escape. But what really happens to the matter that falls in? Some theories suggest that black holes might not destroy information but instead encode it on their surfaces in some unknown way. Others propose that black holes could be linked to other regions of space-time, perhaps even serving as gateways to other universes. If failed supernovae are quietly creating black holes all the time, then they could be shaping the very fabric of space in ways we don't yet understand. This brings us to the ultimate question: if failed supernovae are real, and if they are more common than we think, then what else might be happening in the universe that we simply can't see? What other cosmic events might be occurring in total silence, hidden from view, yet shaping the cosmos in ways we've never even considered? The mystery of failed supernovae isn't just about missing explosions, it's about the unseen forces that sculpt the universe, the invisible objects that may be drifting past us even now, and the unanswered questions that keep astronomers searching the skies. The more we unravel the mystery of failed supernovae, the more unsettling it becomes. If massive stars are silently collapsing into black holes without releasing the expected energy, then the very fabric of our understanding of stellar death needs to be re-examined. What else have we missed? How many of these failed explosions have already occurred, leaving behind nothing but gravitational ghosts? And more importantly, could a star near us be on the verge of such a fate, disappearing before our eyes without a trace? To understand why this is such a big deal, let's think about how we currently track stellar deaths. When a supernova occurs, it sends a powerful shockwave through space, bright enough to be seen across galaxies. We rely on these violent bursts to map the life cycles of stars, to trace elements in the universe, and even to explain the origins of life. After all, many of the elements in our own bodies, like iron and calcium, were forged in the final moments of a supernova explosion. But what if many stars never explode at all? What if they simply vanish into nothingness, cutting off one of the primary ways we understand the cosmos? This concept has already been tested in an attempt to find evidence of failed supernovae. Scientists have monitored specific stars that seem primed to explode, only to find that some of them disappear completely, never producing a visible supernova. One of the most famous cases is N6946 BH1, a massive star in a nearby galaxy that was observed for years. Astronomers expected it to explode, but instead, in 2009, it simply vanished. No explosion. No visible afterglow. Just a bright star that was suddenly gone. The only explanation that fits is that it collapsed directly into a black hole, forming a failed supernova. And if one failed supernova has already been caught in the act, how many more have we missed? The truth is, there could be thousands, maybe even millions, of failed supernovae hiding throughout the cosmos. If a star collapses without an explosion, we wouldn't see it happening. We would only notice the absence of light, a hole where a star used to be. But black holes don't just disappear into the darkness. Over time, they can interact with their surroundings, occasionally feeding on gas, pulling in nearby matter, or merging with other black holes. These quiet, lurking voids may be influencing the structure of galaxies, shaping the cosmic web in ways we've never fully accounted for. This brings us to an even stranger possibility. What if some of these failed supernovae are forming objects that are even weirder than black holes? Some theoretical models suggest that under the right conditions, a collapsing star might form something called a black hole imposter, an object that mimics the properties of a black hole but isn't quite the same. These exotic remnants could have unusual physics, bending space-time in ways we don't yet understand. Could some failed supernovae be producing objects that challenge our entire concept of what happens when a star dies? And then there's the question of what happens to the outer layers of these collapsing stars. In many failed supernova scenarios, the outer shell of the star doesn't immediately collapse. Instead, it might linger for a brief moment before falling inward. This could lead to a strange, short-lived burst of energy, a flickering ghost of a supernova that appears and then vanishes. Some astronomers believe that detecting these faint, temporary signals could be the key to proving that failed supernovae are happening more often than we think. But spotting such an event would be difficult, requiring us to look at the exact right moment before the star disappears forever. Failed supernovae also challenge our understanding of how heavy elements are spread through the universe. If a star collapses without an explosion, then all of the elements it produced remain locked inside the black hole, never released into space. This could mean that some regions of the universe have fewer of the heavy elements needed for life than we expected. If failed supernovae are common, then they could be silently altering the chemical makeup of galaxies, affecting the formation of planets and possibly even the conditions for life. But what if failed supernovae are even more significant than we think? What if they are a key part of some grand cosmic cycle we don't yet understand? There are theories suggesting that black holes might not be the final stage of matter, that they could eventually transform into something else. If so, then failed supernovae might not just be the end of a star, they could be the beginning of an entirely new kind of object. Some physicists even speculate that black holes could evaporate over trillions of years, or that they could lead to the birth of new universes through unknown processes. If that's true, then failed supernovae might be triggering events that shape not just our own universe, but others beyond it. All of this raises one final, haunting question: are failed supernovae happening in ways that we could never detect? What if some of these stellar collapses occur without any observable signals at all? No light, no neutrinos, nothing? It's entirely possible that we are living in a universe where silent, invisible events are happening all around us, rewriting the structure of reality without us ever knowing. And if that's true, then the study of failed supernovae isn't just about understanding stars. It's about confronting the limits of what we can perceive, about accepting that the universe is hiding secrets we may never fully uncover. If failed supernovae are more common than we think, it could mean that many of our calculations about the universe need to be revised. We assume that most massive stars end their lives in a visible explosion, dispersing elements, sending out powerful shockwaves, and leaving behind either a neutron star or a black hole. But what if a significant percentage of stars never go through that process? What if they collapse silently, vanishing into the void without any trace? That would mean our estimates about how many black holes exist, how elements spread through space, and even how galaxies evolve might all be off. One of the biggest implications of failed supernovae is that they might explain why we don't see as many supernovae as we expect. Based on our understanding of how stars live and die, we should be seeing a certain number of supernova explosions every year in our galaxy. But the actual number observed is significantly lower than predicted. This has puzzled astronomers for decades. Could it be that many stars are simply skipping the explosion phase altogether, collapsing straight into black holes without putting on the spectacular light show we expect? If so, then failed supernovae could be happening all around us, and we would have no way of knowing unless we specifically look for the subtle clues they leave behind. This raises another important question: what determines whether a star explodes or fails? Some researchers believe it comes down to the mass of the star and the behavior of its core during collapse. If a star's core doesn't generate enough outward pressure to counteract gravity, it might collapse too quickly for an explosion to occur. In this case, the material surrounding the core would simply fall inward, forming a black hole directly instead of creating a massive explosion. Some models suggest that this could happen in stars that are between 18 and 25 times the mass of our Sun. That's right in the range of many supernova candidates, meaning that a significant number of stars might be undergoing this silent collapse instead of exploding. Another factor could be how much mass the star loses before it dies. Some stars shed a lot of their outer layers through strong stellar winds before they reach the final stage of their lives. If a star loses too much mass, there might not be enough material left to create a powerful enough explosion. Instead of a dramatic supernova, the star might just fizzle out, collapsing in on itself with barely any visible energy released. This could be one reason why some stars that seem close to exploding simply vanish instead of putting on a show. But here's where things get even stranger. Some researchers suggest that failed supernovae could actually create brief, weak flashes of light before the star disappears. In some cases, the outer layers of the star might still get ejected, producing a short-lived, faint explosion before the core collapses into a black hole. This would make it incredibly difficult to detect failed supernovae because they might look like nothing more than a dim flicker in the sky, gone before anyone has a chance to study them. If this is true, it would mean that failed supernovae aren't completely silent. They just don't produce the kind of explosion we're used to seeing. And then there's the question of what happens to the surrounding environment when a failed supernova occurs. In a normal supernova, the explosion sends powerful shockwaves through space, affecting everything around it. These shockwaves can trigger the formation of new stars, shape the structure of galaxies, and even influence the chemistry of interstellar clouds. But if a star collapses silently, none of that happens. The space around the failed supernova remains largely undisturbed, except for the sudden disappearance of a massive object. Could this mean that some regions of space are less active because they are filled with the remnants of failed supernovae, black holes that formed quietly, without triggering the usual cosmic fireworks? If so, then failed supernovae might be one of the hidden forces shaping the evolution of galaxies. Instead of dramatic, explosive events, many stars might simply be vanishing, leaving behind black holes that subtly influence their surroundings over millions of years. This could explain why some galaxies have large numbers of black holes without as many visible supernova remnants as expected. It could also mean that black holes are forming in ways we never fully accounted for, quietly altering the structure of space without any dramatic evidence of their birth. This also brings up a terrifying possibility. Could a nearby star fail to explode and collapse into a black hole without us noticing? If a star in our galactic neighborhood were to undergo a failed supernova, it wouldn't produce a bright explosion that would alert astronomers. Instead, it would simply disappear, leaving behind a black hole that might remain hidden unless it starts pulling in surrounding matter. While black holes don't pose a direct threat to Earth unless they come extremely close, the idea that one could form relatively nearby without us detecting it is unsettling. It would mean that the birth of some of the most extreme objects in the universe is happening right under our noses, beyond our ability to perceive. Some scientists are now looking for ways to detect failed supernovae by searching for their gravitational effects. One possibility is to look for stars that suddenly dim and never recover, signs that they might have collapsed into black holes. Another method is to search for the tiny bursts of energy that might be released just before the final collapse. And with the growing field of gravitational wave astronomy, we might soon be able to detect the ripples in spacetime that occur when a massive star collapses in on itself. If we can find more evidence of failed supernovae, it could change the way we understand the final moments of massive stars, revealing a hidden population of black holes that have been forming silently for billions of years. But what if there's an even bigger mystery at play? What if some failed supernovae don't just collapse into black holes but instead form something else, something we don't yet understand? Some exotic theories suggest that under certain conditions, a collapsing star could create an object even stranger than a black hole. One possibility is the formation of black hole imposters, hypothetical objects that mimic black holes but have different internal structures. Another idea is that failed supernovae could produce exotic stars made of unknown forms of matter, hidden from view because they don't emit the kind of radiation we're used to detecting. If such objects exist, they could be scattered throughout the universe, masquerading as black holes while actually being something entirely different. This could mean that some of the black holes we think we've detected might not be black holes at all, but instead failed supernova remnants that have taken on unexpected forms. The implications of this would be staggering. forcing us to reconsider everything we thought we knew about how stars die and what they leave behind. We have to ask, could failed supernovae be connected to some of the biggest cosmic mysteries we haven't solved yet? Could they be responsible for unexplained gamma-ray bursts, strange radio signals, or even the odd behavior of dark matter? If failed supernovae are forming unusual objects, then they might be creating phenomena that we currently don't have an explanation for. The more we study these mysterious stellar collapses, the more questions arise. How many stars are failing to explode right now, beyond our ability to detect? How many hidden black holes or other strange objects have already formed in the depths of space, waiting to be discovered? And what do these silent deaths tell us about the nature of the universe itself? The truth is, we are only beginning to scratch the surface of this mystery, and as our tools and understanding improve, we may find that failed supernovae hold the key to unlocking some of the greatest secrets of the cosmos. Failed supernovae might be one of the most underestimated phenomena in astrophysics, but what if they play a much larger role in shaping the universe than we ever imagined? If a significant number of massive stars collapse directly into black holes without an explosion, that would mean that black holes are forming at a rate far higher than previously thought. This would have massive implications for our understanding of cosmic evolution. Galaxies are shaped by the presence of black holes, and their gravitational influence extends far beyond their immediate surroundings. If failed supernovae are more common than we expect, then black holes may be forming in clusters, altering the gravitational landscape of entire regions of space. But how do we know these failed supernovae are even happening? One of the most compelling pieces of evidence comes from disappearing stars. A star that is on the verge of a supernova should be incredibly bright, and astronomers have identified numerous candidates that seem like they are nearing the end of their life cycle. However, in some cases, these stars have simply vanished from view without any sign of an explosion. In one particularly striking case, a massive star in the nearby galaxy NGC 6946 was observed for years as it approached its final stages. Then, suddenly it was gone. No bright supernova, no glowing remnants, just darkness where the star had once been. This event has led researchers to suspect that it collapsed straight into a black hole without an explosion. If this is true, then similar events could be happening across the universe all the time, unseen and unnoticed. Some scientists estimate that as many as 10 to 30% of all massive stars might undergo failed supernovae instead of exploding. That means that for every 10 supernovae we see, there could be several more that happen invisibly, contributing to the growing population of black holes. This realization has led to new efforts to detect failed supernovae by looking for indirect evidence. One method is to look at the stars surrounding a suspected failed supernova. If a massive star collapses directly into a black hole, it might exert a sudden gravitational pull on nearby objects, slightly altering their orbits. By studying these changes, astronomers might be able to pinpoint the locations of newly formed black holes. Another approach involves searching for brief flashes of light that could be created if some material is ejected before the collapse. These flashes would be far weaker than a typical supernova and would fade quickly, making them incredibly difficult to spot. But failed supernovae don't just raise questions about black hole formation. They also challenge our understanding of the distribution of elements in the universe. Normal supernovae play a crucial role in spreading heavy elements like iron, gold, and uranium throughout space. These elements are created in the intense heat and pressure of a supernova explosion and are then scattered into interstellar clouds, where they eventually become part of new stars and planets. If many stars are collapsing into black holes without exploding, then those heavy elements are being trapped inside the black hole instead of being released into space. This could mean that certain elements are less common in some regions of the universe than we expected, simply because many stars failed to go supernova. And if failed supernovae are more common in certain types of galaxies, that could mean those galaxies have fewer of the heavy elements needed to form rocky planets. This, in turn, could have consequences for the likelihood of life developing in different parts of the universe. If heavy elements are essential for life as we know it, then galaxies where failed supernovae are common might have far fewer habitable planets than galaxies where more stars explode and spread their material. Even more intriguingly, failed supernovae could provide a missing piece of the puzzle when it comes to understanding long-duration gamma-ray bursts. These bursts are some of the most energetic events in the universe, releasing more energy in a few seconds than the Sun will emit in its entire lifetime. They are typically associated with the deaths of massive stars, but there are cases where they don't seem to fit the expected pattern of a typical supernova. Some researchers now suspect that certain gamma-ray bursts might be linked to failed supernovae, where the collapse of the star creates a brief but powerful burst of energy before the black hole fully forms. If this is true, then failed supernovae could be influencing not just the formation of black holes, but also some of the most extreme high-energy events in the cosmos. But what if failed supernovae don't always result in black holes? Some theories suggest that under certain conditions, the core of a collapsing star could reach a state where it resists further collapse, forming something even stranger than a neutron star or a black hole. One possibility is the formation of a quark star, a hypothetical object where the extreme pressure forces protons and neutrons to break down into their fundamental components, creating a dense sea of quarks. If quark stars exist, they could be hiding in plain sight, mistaken for either neutron stars or black holes because of their extreme density and compact size. Another even more exotic possibility is the creation of a so-called gravistar. This is a theoretical object proposed as an alternative to black holes, where the collapsing core of a star forms a bubble of exotic energy instead of a singularity. In this model, a gravistar would appear similar to a black hole from the outside, but instead of having an event horizon, it would have a shell of highly compressed matter that prevents anything from falling in or escaping. If such objects exist, then failed supernovae might be producing them alongside black holes, adding yet another layer of complexity to the already mysterious process of stellar death. Even with all of these theories, one of the biggest challenges in studying failed supernovae is simply the lack of observational data. Traditional telescopes rely on detecting light, and failed supernovae, by definition, don't produce much visible radiation. However, the rise of new observational methods, such as neutrino detection and gravitational wave astronomy, might finally allow us to detect these silent stellar deaths. Neutrinos are nearly massless particles that are produced in vast quantities during a star's collapse, and they can pass through space undisturbed, making them a potential tool for detecting failed supernovae. Similarly, gravitational waves, ripples in space-time created by massive cosmic events, could provide another way to detect the formation of black holes from failed supernovae. In the coming years, as technology improves, we might finally be able to identify these ghostly stellar collapses and answer some of the biggest questions surrounding them. How often do they occur? What determines whether a star explodes or collapses silently? And what hidden consequences do they have for the universe at large? One thing is certain, failed supernovae may be silent, but they are far from insignificant. They could be shaping the cosmos in ways we never imagined, influencing the formation of black holes, the distribution of elements, and even the very structure of galaxies. If failed supernovae are happening all around us, beyond the reach of our current telescopes, then we are living in a universe filled with unseen cosmic events. Stars are dying without a sound, leaving behind invisible marks on the fabric of space. Black holes are forming in the shadows, waiting to be discovered. And as we continue to push the boundaries of astronomy, we may one day uncover the full story of these silent stellar deaths. Until then, failed supernovae remain one of the greatest unsolved mysteries of the cosmos, an enigma hiding in plain sight, waiting for the right observer to finally reveal its secrets. Failed supernovae might seem like a minor detail in the vast universe, but they could hold answers to some of the biggest cosmic mysteries. If these silent collapses are as common as some scientists predict, then black holes might be forming in much greater numbers than we previously assumed. This has major implications for how galaxies evolve, how matter is distributed across the cosmos, and even how we understand the ultimate fate of the universe. One of the most intriguing possibilities is that failed supernovae could explain the existence of intermediate mass black holes. These are black holes that are larger than stellar mass black holes, which form from typical supernovae, but smaller than the supermassive black holes that exist at the centers of galaxies. intermediate mass black holes have been one of the most elusive objects in astrophysics. Scientists suspect they exist, but finding direct evidence has been extremely difficult. If large stars are collapsing straight into black holes without an explosion, they could be creating black holes that are larger than the usual stellar mass variety. Over time, these black holes could merge with others, forming the missing link between small black holes and the supermassive giants. But what if failed supernovae are even more common than we think? Some models suggest that the rate of these silent collapses could be significantly underestimated. If that's the case, then our entire understanding of how elements spread through the universe might need to be reconsidered. When a star undergoes a traditional supernova, it spreads elements like iron, gold, and uranium into space. These heavy elements eventually form new stars, planets, and even the building blocks of life. But if many massive stars are collapsing directly into black holes without an explosion, then these elements are being locked away forever inside the black hole, never to be spread into space. This could mean that certain regions of the universe are less enriched with heavy elements than we expected. In turn, this could affect the formation of planets and, potentially, life itself. If a galaxy has a high number of failed supernovae, then it might have fewer rocky planets, since those require heavy elements like iron and silicon. And if planets with the right chemical composition for life are rarer in these regions, then that could mean that life is less common in certain parts of the cosmos. In a way, failed supernovae might be indirectly shaping the distribution of habitable planets across the universe. But there's another layer to this mystery that makes it even more intriguing. If failed supernovae are common, then the number of isolated black holes drifting through the galaxy could be far higher than we assume. Typically, when we think of black holes, we imagine them at the centers of galaxies or as part of binary star systems, where they interact with a companion star. However, a failed supernova could create a rogue black hole, a black hole that forms in isolation and simply drifts through space, invisible to our telescopes. These rogue black holes could number in the millions or even billions, wandering undetected through the Milky Way. Occasionally, a rogue black hole might pass in front of a distant star, causing a phenomenon known as gravitational microlensing. This happens when the intense gravity of the black hole bends and magnifies the light from the background star, briefly making it appear brighter. Scientists have already detected several mysterious microlensing events that could have been caused by rogue black holes, but confirming their presence is extremely difficult. If failed supernovae are creating vast numbers of these wandering black holes, then they might be far more common than we ever imagined. There is also a more extreme possibility to consider. What if some failed supernovae are not forming black holes at all? Some researchers believe that in certain cases, the collapsing core of a star might stabilize at an incredibly high density, creating an object even stranger than a neutron star. One possibility is a quark star, a hypothetical object where the extreme pressure breaks protons and neutrons into their fundamental components, forming a dense soup of quarks. If quark stars exist, they could be hiding among the neutron stars we already know about, and failed supernovae might be responsible for their formation. But even more bizarre is the idea that some failed supernovae might create exotic objects known as gravastars. These theoretical objects have been proposed as an alternative to black holes, where the collapsing core of a star forms a shell of exotic energy instead of a singularity. From the outside, a gravastar would look almost identical to a black hole, but it would have a fundamentally different internal structure. If gravastars exist, then failed supernovae might be producing them alongside black holes, adding yet another layer of mystery to these silent stellar deaths. There is also the question of what role failed supernovae might play in the mysterious origins of long-duration gamma-ray bursts. These are some of the most energetic events in the universe, capable of releasing more energy in a few seconds than the sun will emit in its entire lifetime. Typically, gamma-ray bursts are thought to be linked to the deaths of massive stars, but some of them do not seem to fit the expected pattern of a traditional supernova. Some scientists now suspect that failed supernovae might be responsible for certain types of gamma-ray bursts, where the collapse of a star briefly creates a powerful jet of energy before the black hole fully forms. But how can we actually confirm that failed supernovae are happening? Since they don't produce a bright explosion, They are incredibly difficult to observe directly. However, scientists have developed several strategies to detect them. One method involves searching for disappearing stars. If a star nearing the end of its life simply vanishes without producing a visible explosion, that could be a sign that it has collapsed into a black hole without a supernova. Several candidates for failed supernovae have already been identified this way, where stars that were once bright have seemingly disappeared into darkness. Another approach involves looking for brief flashes of light that might be produced if some material is ejected before the star collapses. These flashes would be much weaker than a normal supernova and would fade quickly, making them incredibly difficult to spot. Scientists are now using specialized telescopes to search for these faint signals in an attempt to catch failed supernovae in the act. There is also hope that new technologies like neutrino detectors and gravitational wave observatories could provide crucial evidence. When a star collapses, it produces a flood of neutrinos, tiny, nearly massless particles that pass through space undisturbed. If a failed supernova produces a sudden burst of neutrinos without a corresponding supernova explosion, that could be a clear sign that a silent collapse has occurred. Similarly, gravitational wave detectors like LIGO and Virgo might be able to pick up signals from these events, providing another way to detect failed supernovae indirectly. As our technology improves, we may finally be able to answer some of the biggest questions about failed supernovae. How often do they occur? What determines whether a star explodes or collapses silently? And what hidden consequences do they have for the universe as a whole? One thing is certain: failed supernovae may be invisible, but they are not insignificant. They could be shaping the cosmos in ways we have yet to fully understand, influencing the formation of black holes, the distribution of elements, and even the very structure of galaxies. If failed supernovae are happening all around us, beyond the reach of our current telescopes, then we are living in a universe filled with unseen cosmic events. Stars are dying without a sound, leaving behind invisible marks on the fabric of space. Black holes are forming in the shadows, waiting to be discovered. And as we continue to push the boundaries of astronomy, we may one day uncover the full story of these silent stellar deaths. Until then, failed supernovae remain one of the greatest unsolved mysteries of the cosmos, an enigma hiding in plain sight, waiting for the right observer to finally reveal its secrets. Failed supernovae might be the key to unlocking some of the biggest mysteries in astrophysics, but their very nature makes them elusive. Since they leave behind no bright explosions, no dramatic light shows, and often no direct signs of their existence, they remain hidden in the vast darkness of space. But what if we could change that? What if we had the right tools, the right observations, and the right methods to finally uncover these silent collapses? As technology advances, astronomers are getting closer than ever to proving the reality of failed supernovae, and the discoveries they make could change everything we thought we knew about how stars die, how black holes form, and how the universe itself evolves. One of the biggest challenges in identifying failed supernovae is that they often take place in distant galaxies, far beyond the reach of most telescopes. However, astronomers have developed new strategies to track them down. One of the most promising methods is long-term monitoring of red supergiant stars, the massive stars that are expected to either explode as supernovae or collapse silently. By observing these stars over time, scientists can look for signs that a star has vanished without an explosion. If a massive star is shining brightly one year and is simply gone the next, with no remnant of a supernova, that could be a strong indication that a failed supernova has occurred. This method has already yielded some intriguing results. In 2017, astronomers studying the galaxy NGC 6946, a galaxy known for its frequent supernovae, noticed that a massive red supergiant star appeared to have disappeared without a trace. The star, known as N6946BH1, had been observed for several years and showed signs of instability, suggesting it was nearing the end of its life. Then, without warning, it simply faded away. No bright explosion was detected, no supernova remnants were left behind. It was as if the star had been swallowed by the darkness, never to be seen again. This discovery provided one of the strongest pieces of evidence yet for the existence of failed supernovae. If N6946BH1 truly collapsed into a black hole without an explosion, then it suggests that failed supernovae are not just theoretical. They are real, and they are happening in the universe right now. But this is just the beginning. Astronomers are now expanding their search, monitoring thousands of massive stars across multiple galaxies to see if more of them vanish in the same way. If they do, then failed supernovae may turn out to be far more common than we ever imagined. But what exactly causes a star to undergo a failed supernova instead of a traditional supernova? The answer lies in the delicate balance between gravity and nuclear fusion. Throughout a star's life, nuclear fusion generates energy that counteracts the immense force of gravity trying to collapse the star inward. But when the star runs out of fuel, gravity wins. In a typical supernova, this collapse triggers a massive explosion, ejecting the outer layers of the star into space. However, in a failed supernova, the collapse continues inward, and instead of exploding, the star's core forms a black hole almost instantly. The reason for this difference comes down to mass and energy. Some stars are simply too massive for an explosion to occur. In these cases, the core collapses so rapidly that the energy required to trigger a supernova never fully develops. Instead of rebounding and ejecting material outward, the entire structure collapses inward, trapping all of its mass within the event horizon of a newly formed black hole. This process happens so quickly that there is almost no time for an explosion to take place, leaving behind nothing but darkness. However, some scientists believe that failed supernovae might not always be entirely silent. In certain cases, there could be a brief burst of light or energy just before the collapse. Some models suggest that a dying star might release a last-minute pulse of weak radiation or a short-lived flash of neutrinos before disappearing forever. If this is true, then we might be able to detect these fleeting signals and use them to confirm the presence of failed supernovae. One possible way to do this is by looking for unusual infrared signals. When a star collapses, some of its outer material might still be ejected, but in much smaller amounts than in a full supernova. This ejected material could emit faint infrared radiation as it cools down, creating a weak but detectable signature. Scientists are now using infrared telescopes to search for these signals, hoping to catch a glimpse of a failed supernova in action. Another promising method involves neutrino detection. Neutrinos are nearly massless subatomic particles that can pass through matter almost undisturbed. During a core collapse, a massive burst of neutrinos is released, even if no explosion occurs. If scientists can detect a sudden spike in neutrinos from a dying star without seeing a corresponding supernova, that could be a major clue that a failed supernova has taken place. This is where facilities like the Super Kamiokande detector in Japan and the IceCube Neutrino Observatory in Antarctica come into play. These massive underground detectors are designed to capture rare neutrino interactions, providing valuable insights into astrophysical events. If a nearby massive star were to undergo a failed supernova, these detectors might be able to pick up the burst of neutrinos it emits. This could serve as direct proof that failed supernovae are real and happening more frequently than we thought. Gravitational wave observatories like LIGO and Virgo could also help solve this mystery. When a massive object collapses into a black hole, it can create ripples in the fabric of space-time known as gravitational waves. If a failed supernova produces a sudden burst of gravitational waves, these observatories might be able to detect it, giving us yet another way to confirm the existence of these silent collapses. The implications of failed supernovae go far beyond just black holes. If they are common, they could have a significant impact on the chemical evolution of the universe. Supernovae are responsible for spreading heavy elements like iron, gold, and uranium into space, enriching future generations of stars and planets. But if a large number of stars are collapsing directly into black holes without exploding, then many of these elements could be getting locked away forever. This could mean that certain regions of the universe have far fewer heavy elements than we expect, potentially affecting everything from planet formation to the possibility of life. Failed supernovae might also play a role in explaining some of the strangest objects in the cosmos, like intermediate mass black holes. These black holes, which are larger than typical stellar mass black holes but smaller than supermassive black holes, have been incredibly difficult to detect. If failed supernovae can create black holes that are larger than normal, then they could provide a natural explanation for how intermediate mass black holes form. Even more intriguing is the possibility that some failed supernovae might not create black holes at all. Some scientists have proposed that under extreme conditions, a collapsing star might form an exotic object like a quark star or a gravistar instead. These hypothetical objects could be even stranger than black holes, with bizarre properties that challenge our understanding of physics. If failed supernovae are producing these mysterious remnants, then we might need to completely rethink what happens when massive stars die. Ultimately, the study of failed supernovae is still in its early stages, but the evidence is growing. As new observations are made and new technologies come online, we may finally be able to unravel this cosmic mystery. If failed supernovae are as common as some models suggest, then they could be shaping the universe in ways we never imagined. They could be silently influencing the formation of black holes, the distribution of elements, and even the conditions for life itself. For now, failed supernovae remain one of the greatest unsolved puzzles in astrophysics. They are the silent deaths of stars, the hidden architects of the cosmos, and the missing link in our understanding of stellar evolution. As we continue to explore the universe, one thing is certain: these invisible events may hold the answers to some of the biggest questions in science. Failed supernovae challenge our fundamental understanding of how stars die and what happens in the final moments before collapse. For decades, astronomers believed that the fate of a massive star was straightforward. Once it exhausted its nuclear fuel, it would either explode in a spectacular supernova or quietly shed its outer layers to form a white dwarf. But the discovery of failed supernovae suggests that reality is far more complex. The idea that some stars simply vanish without an explosion forces us to rethink everything we thought we knew about stellar death, black hole formation, and the very structure of the universe itself. One of the most perplexing questions surrounding failed supernovae is, how often do they occur? If they are extremely rare, then they may have little impact on the broader structure of the cosmos. But if they are common, they could fundamentally alter our understanding of how galaxies evolve. Some studies suggest that as many as 1 in 3 massive stars might collapse into a black hole without an explosion. If true, this means that the universe is filled with invisible deaths, stars that lived for millions of years, shining brightly, only to disappear in an instant without a trace. The best way to determine how common failed supernovae are is through systematic surveys of massive stars. Astronomers have already begun long-term monitoring projects, tracking red supergiants in nearby galaxies to see if any of them vanish without producing a visible supernova. By comparing the number of disappearing stars to the number of confirmed supernovae, scientists can estimate the true rate of failed supernovae. Early results suggest that these events may be surprisingly frequent, hinting that black hole formation through direct collapse could be a dominant process in the universe. But failed supernovae don't just affect black holes. They could also play a key role in the overall chemical makeup of the cosmos. Traditional supernovae are responsible for dispersing heavy elements like carbon, oxygen, and iron into space, enriching future generations of stars and planets. If a significant fraction of massive stars undergo failed supernovae instead, this could mean that many of these elements are being locked away inside black holes, never to be released into the universe. This could help explain certain anomalies in the chemical composition of galaxies, where some regions appear to have far fewer heavy elements than expected. There is also a growing suspicion that failed supernovae might be linked to another astrophysical mystery: long-duration gamma-ray bursts. These intense bursts of high-energy radiation come from distant galaxies and are thought to be caused by the collapse of massive stars. However, in some cases, astronomers have detected gamma-ray bursts without a corresponding supernova. One possibility is that these bursts are the last dying signals of failed supernovae, brief flashes of energy released as a star collapses directly into a black hole. If this is true, then gamma-ray bursts could serve as another way to detect failed supernovae and study their properties. The more we learn about failed supernovae, the more questions arise. Do they always form black holes, or can they sometimes produce other exotic objects like quark stars? Could some failed supernovae produce faint, undetectable explosions instead of complete collapses? And what role do they play in shaping galaxies over cosmic time? Answering these questions will require a new generation of telescopes and detectors, capable of peering deeper into the universe and capturing the faint signals of these mysterious events. As technology advances, our ability to detect failed supernovae will only improve. Upcoming observatories like the Vera C. Rubin Observatory will be able to monitor millions of stars across the sky, searching for sudden disappearances. Meanwhile, next-generation neutrino detectors and gravitational wave observatories will provide new ways to track the invisible signatures of stellar collapse. With each new discovery, we come closer to uncovering the full story of failed supernovae, and with it, a deeper understanding of the universe itself. The implications of failed supernovae extend beyond astrophysics. They force us to confront the idea that the universe is filled with hidden processes, events that occur without leaving obvious clues. If so many massive stars can vanish without an explosion, what other cosmic events might be slipping past our detection? What other secrets does the universe hold, waiting for us to discover them? The search for failed supernovae is not just about studying the death of stars, it is about uncovering the unseen forces that shape the cosmos. As we continue to push the boundaries of astronomical research, failed supernovae remain one of the most intriguing unsolved mysteries in science. They are the missing piece of the puzzle, the silent architects of the universe, and a reminder that even the most familiar cosmic events can still surprise us. The more we look, the more we realize that the universe is far stranger than we ever imagined, and the mystery of failed supernovae is just one of the many enigmas waiting to be solved. The search for failed supernovae is not just about confirming their existence, it's about understanding their mechanics, their impact on galaxies, and what they reveal about the fundamental forces that govern the cosmos. One of the most pressing questions is what determines whether a massive star will explode as a supernova or collapse directly into a black hole. The line between these two outcomes is still blurry, but scientists believe it has to do with the core mass, rotation, and the amount of energy available to trigger an explosion. In a typical core collapse supernova, the iron core of a massive star reaches a critical mass and collapses under its own gravity. This collapse releases an enormous amount of energy, which rebounds off the dense core and launches an explosion that rips apart the star. However, in some cases, the collapse does not generate enough outward force to trigger an explosion. Instead, the core continues to collapse inward, forming a black hole without a supernova. This is what astronomers refer to as a failed supernova. One major factor that determines whether a supernova occurs is the role of neutrinos. These nearly massless particles are produced in vast quantities during the collapse of a star's core. In a normal supernova, neutrinos carry away energy, but they also help power the explosion by heating the outer layers of the star. If the core absorbs too many neutrinos before they escape, the explosion might fail, and the entire star could collapse inward. Another key factor is the star's mass. Most failed supernovae are expected to come from stars with masses above 20 to 25 times the mass of the Sun. Below this threshold, supernova explosions are more likely to succeed because the outer layers of the star are not as tightly bound. But in more massive stars, gravity is so strong that even the immense energy of a collapsing core might not be enough to trigger an explosion. There's also evidence that failed supernovae could be linked to rapid rotation. Some models suggest that stars spinning at high speeds could create conditions that prevent a successful explosion. In these cases, the collapse might form a rapidly spinning black hole, potentially launching a jet of material that escapes along the star's axis. If this jet is not strong enough to blow apart the star, it could result in a failed supernova, leaving behind only a black hole and a brief burst of radiation. But failed supernovae are not always completely invisible. Some may produce a brief flash of light as their outer layers fall onto the newly formed black hole. This phenomenon, sometimes called a fallback supernova, occurs when the material surrounding the collapsing core doesn't escape entirely. Instead, it briefly forms an accretion disk before being swallowed by the black hole. This process could produce a faint burst of energy, detectable with sensitive telescopes. There's also a possibility that failed supernovae could generate gravitational waves. When a supernova explodes asymmetrically, it can send ripples through spacetime, which we detect as gravitational waves. If a failed supernova involves the rapid collapse of a spinning core, it could produce a distinct gravitational wave signal, one that might provide new insights into how black holes form. One of the most famous suspected failed supernova candidates is N6946bh1, a red supergiant star in the galaxy NGC 6946. This star was observed for years before it suddenly vanished in 2009. No supernova explosion was detected, and deep follow-up observations found only a faint infrared glow, possibly the last remnant of the collapsing star. If confirmed, this would be the first direct evidence of a failed supernova, proving that massive stars can indeed collapse into black holes without a visible explosion. The implications of failed supernovae go beyond individual stars. They affect the overall black hole population in the universe, influencing how many stellar mass black holes exist and how they merge over time. If failed supernovae are common, it could explain why we detect so many black hole mergers through gravitational waves. Instead of forming through the explosion of a supernova, many black holes might be forming quietly through direct collapse, only to merge millions of years later. Failed supernovae could also help solve the missing supernova problem. Based on the number of massive stars observed in the Milky Way and nearby galaxies, astronomers have long expected to see more supernovae than they actually detect. The simplest explanation is that many of these stars don't explode at all. They just collapse into black holes. If true, then failed supernovae might be a crucial missing piece in our understanding of stellar evolution. Despite their elusive nature, failed supernovae could become easier to detect in the future. Advanced telescopes like the James Webb Space Telescope, JWST, and the Extremely Large Telescope, ELT, will be able to monitor distant galaxies with unprecedented precision, looking for the telltale disappearance of massive stars. Meanwhile, next-generation neutrino and gravitational wave observatories could provide indirect evidence of these events, helping scientists piece together the full picture of how stars die. The study of failed supernovae is still in its early stages, but it has already reshaped our understanding of stellar death. What was once thought to be a rare, exotic phenomenon might actually be a common outcome for massive stars. If so, it means that much of the universe's black hole population was created not through the violent explosions of supernovae, but through silent, unseen collapses. As our technology improves, we may soon witness the first confirmed failed supernova in real time, watching as a massive star simply vanishes into darkness, leaving behind no explosion, no nebula, just a black hole silently forming where a brilliant star once shined. And when that moment comes, it will mark not just the discovery of a long-theorized event, but a profound new understanding of the universe's hidden mechanisms. Failed supernovae challenge our traditional view of how massive stars die, suggesting that many of them might simply disappear into black holes without a dramatic explosion. This realization has profound implications for astrophysics, from the formation of black holes to the chemical enrichment of galaxies. If more stars collapse directly instead of exploding, it means fewer heavy elements like iron, nickel, and gold are released into space, elements that are crucial for forming planets and even life itself. This raises an intriguing question. Could failed supernovae be shaping the cosmic distribution of elements in ways we don't yet understand? To grasp the full impact of failed supernovae, let's dive deeper into the physics behind them. The key to a successful supernova is a mechanism known as the core bounce. When a massive star reaches the end of its life, it burns through its nuclear fuel, leaving behind an iron core. Unlike lighter elements, iron cannot be fused into heavier elements to release energy, so the core loses its internal pressure and collapses under gravity. In a normal supernova, the collapse halts when the core reaches nuclear densities, causing it to bounce back outward. This rebound generates an immense shockwave that tears the star apart. But in a failed supernova, this bounce is weak or non-existent. Instead of reversing the collapse, the core continues to shrink, eventually forming a black hole. The energy that would have powered an explosion is instead swallowed by the forming singularity, leaving behind nothing but darkness. This process happens so quickly that the outer layers of the star don't have time to react in the dramatic way we expect from a supernova. Instead, they may either fall silently onto the black hole or drift away as a faint, slow-moving cloud of gas. One of the biggest mysteries surrounding failed supernovae is whether they are truly silent, or if they produce any detectable signals. While traditional telescopes may not see an explosion, other methods could reveal their presence. For example, when a star collapses into a black hole, it should produce a flood of neutrinos, nearly massless particles that barely interact with matter. Neutrino observatories, like IceCube in Antarctica and Super Cameo Candy in Japan, might one day detect a burst of these ghostly particles from a failed supernova, confirming its existence. Another potential clue comes from gravitational waves. When a core collapse supernova occurs, it often generates asymmetric shock waves that send ripples through space-time. A failed supernova might create a distinct gravitational wave signature if the collapsing star rotates rapidly or experiences turbulent motion during its final moments. Future gravitational wave observatories, such as the proposed Einstein telescope and the Laser Interferometer Space Antenna, LISA, could provide the first direct evidence of these elusive events. But what about the outer layers of the star? If they don't explode outward in a traditional supernova, where do they go? In some cases, they may slowly fall onto the black hole over time, creating an accretion disk that emits faint X-rays or infrared radiation. This slow decay of the star's outer envelope could explain the faint afterglow observed in some suspected failed supernovae, such as N6946BH1. There's also the possibility that some failed supernovae might be only partially failed. Instead of completely collapsing in on themselves, some stars might undergo a weak explosion that ejects only a small portion of their outer layers while the core collapses into a black hole. This could create a kind of ghost supernova, a dim, fading event that doesn't resemble the bright, powerful explosions we typically associate with dying stars. One of the most intriguing ideas surrounding failed supernovae is their connection to long-duration gamma-ray bursts, GRBs. These are some of the most energetic explosions in the universe, often associated with the deaths of massive stars. Some scientists believe that a rapidly spinning star collapsing directly into a black hole could generate a gamma-ray burst through the formation of a powerful jet. If this jet fails to break through the outer layers of the star, it might produce only a brief flash of radiation, hinting at a failed supernova hidden beneath. The potential link between failed supernovae and gamma-ray bursts could help explain why some GRBs appear much fainter than expected. Instead of coming from a successful explosion, they might originate from a star that collapsed almost entirely into a black hole, with only a small burst of energy escaping before the event horizon swallowed everything else. But failed supernovae don't just affect individual stars. They also shape the evolution of entire galaxies. When a supernova explodes, it releases heavy elements and high-energy radiation that influence the surrounding interstellar medium. If a large fraction of massive stars collapse without exploding, it could mean that some galaxies receive less enrichment from supernova ejecta. This, in turn, could impact future generations of stars and planets, potentially altering the conditions for habitability in different regions of the cosmos. There's also the question of how failed supernovae influence black hole demographics. If many massive stars collapse directly into black holes, it could explain why we observe so many stellar mass black holes in the universe. Traditional supernovae are expected to leave behind neutron stars in some cases, but if failed supernovae are common, it might mean that black holes form much more frequently than previously thought. This could have major implications for our understanding of black hole mergers. The gravitational wave detections from LIGO and Virgo suggest that many black hole pairs merge over time, releasing enormous amounts of energy in the process. If failed supernovae are responsible for forming a large portion of these black holes, it could mean that direct collapse black holes play a more significant role in shaping the universe than we ever imagined. One of the most fascinating aspects of failed supernovae is their connection to red supergiants, the massive, bloated stars that are often thought to be the progenitors of Type II supernovae. Observations of red supergiants disappearing without an accompanying explosion suggest that some of them may be collapsing directly into black holes. If this is true, then the way we classify supernova progenitors might need to be revised. Current supernova models assume that most massive stars will eventually explode, but if a significant fraction instead undergoes failed supernovae, it could mean that many stars we previously expected to produce bright explosions will instead vanish quietly. This could explain why certain types of supernovae appear less frequently than models predict. Failed supernovae also raise questions about the final stages of stellar evolution. If some stars skip the explosion phase entirely, it means there could be a hidden population of massive stars that simply fade away without a trace. These stars might be lurking in the datasets of observatories that have monitored galaxies for decades, waiting to be identified through careful analysis of archival data. One of the best ways to confirm failed supernovae is through long-term monitoring of massive stars. By keeping a close watch on thousands of red supergiants and other massive stars, astronomers hope to catch one in the act of vanishing. If a star is seen to dim and disappear without a corresponding supernova, it would provide the strongest evidence yet for failed supernovae. Future space telescopes, such as the Nancy Grace Roman Space Telescope and the Vera C. Rubin Observatory, will play a crucial role in this search. These telescopes will be capable of scanning large portions of the sky with high sensitivity, making it easier to identify stars that suddenly vanish without a trace. Ultimately, failed supernovae represent one of the biggest open questions in astrophysics. They challenge our understanding of stellar death, black hole formation, and the very nature of cosmic evolution. If these events are as common as some models suggest, it means that a significant portion of the universe's most massive stars are quietly collapsing into darkness, hidden from view. And yet, with each new observation, each new gravitational wave detection, and each new breakthrough in neutrino astronomy, we are getting closer to uncovering the true nature of these ghostly events. One day, we may finally witness the moment when a massive star vanishes into nothingness, a silent, invisible death that leaves behind only a black hole and a universe forever changed by its passing. Failed supernovae challenge one of the most fundamental assumptions in astrophysics, that the deaths of massive stars are always dramatic. The idea that some stars simply collapse into black holes without an explosion forces us to rethink our understanding of stellar evolution and the life cycle of galaxies. But the implications of failed supernovae go beyond just individual stars. They could also be key to understanding some of the greatest cosmic mysteries, including the formation of the first black holes, the origins of high-energy cosmic phenomena, and even the overall structure of the universe itself. One of the biggest open questions in modern astrophysics is how supermassive black holes, millions or even billions of times the mass of the Sun, formed in the early universe. According to current models, black holes grow by slowly accreting gas or by merging with other black holes over time. However, observations of the distant universe suggest that some supermassive black holes existed when the universe was less than 1 billion years old, meaning they must have grown much faster than traditional accretion models allow. This is where failed supernovae could play a crucial role. If a significant fraction of the first generation of massive stars collapsed directly into black holes, it could have created a population of seeds for supermassive black holes to grow from. Unlike black holes formed from traditional supernovae, these direct collapse black holes could start their existence with much larger masses, allowing them to reach supermassive scales in a much shorter period. This could help explain why quasars, extremely bright, active galactic nuclei powered by supermassive black holes, appear so early in the universe's history. The connection between failed supernovae and early black hole formation also ties into another cosmic puzzle: the distribution of elements in the universe. Supernovae are responsible for creating and dispersing heavy elements like carbon, oxygen, and iron, which are essential for forming planets and life. If failed supernovae are more common than we expect, it could mean that some regions of the universe received far less enrichment from supernova explosions than others. This could lead to variations in the composition of galaxies and star-forming regions, potentially influencing the conditions for planet formation and even the likelihood of life emerging in different parts of the cosmos. Another intriguing aspect of failed supernovae is their potential role in explaining dark collapses, events where a star disappears without any visible explosion. In recent years, astronomers have been monitoring thousands of massive stars in nearby galaxies, searching for supernovae. In some cases, stars that were previously visible in telescope surveys have simply vanished without a trace. These missing stars are some of the strongest observational evidence for failed supernovae, suggesting that at least some massive stars end their lives by collapsing directly into black holes. One of the most famous candidates for a failed supernova is the star N6946bh1, located in the galaxy NGC 6946. This star, a red supergiant about 25 times the mass of the Sun, was observed to gradually fade between 2009 and 2015 without producing a detectable supernova. Follow-up observations with the Hubble Space Telescope and the Spitzer Space Telescope found no sign of a surviving star, suggesting that it had collapsed into a black hole without an explosion. If this event was indeed a failed supernova, it provides direct evidence that some massive stars bypass the traditional supernova process entirely. The case of N6946bh1 also raises another question. What fraction of massive stars experience failed supernovae instead of successful explosions? Current estimates suggest that anywhere from 10% to 30% of core-collapse supernovae could actually be failed supernovae. However, this number is still uncertain, and future observations will be needed to refine it. If failed supernovae are as common as some models suggest, it could mean that black holes form much more frequently than we currently believe. This, in turn, has implications for our understanding of black hole mergers. The detection of gravitational waves by LIGO and Virgo has revealed that black holes frequently merge, producing powerful ripples in spacetime. If failed supernovae are responsible for forming a significant fraction of these black holes, it could help explain why we observe so many binary black hole mergers. It also suggests that some black hole mergers might be occurring in regions where traditional supernova models wouldn't predict them, such as low metallicity environments where massive stars are less likely to lose mass before collapsing. Failed supernovae might also help explain the existence of intermediate mass black holes, which are larger than stellar mass black holes but smaller than supermassive black holes. These black holes, with masses between 100 and 100,000 times that of the Sun, have long been difficult to explain using traditional supernova models. If failed supernovae can produce black holes with masses in this range, it could provide a natural explanation for how these intermediate mass black holes form. Another key question is whether failed supernovae leave behind any detectable remnants. In some cases, the outer layers of the collapsing star might not fall directly into the black hole, but instead form a slow-moving cloud of gas. If this happens, it could create a faint, long-lived afterglow that astronomers might be able to detect using infrared or radio telescopes. Some researchers have proposed searching for these faint remnants in nearby galaxies to identify more examples of failed supernovae. Additionally, failed supernovae might leave behind subtle signatures in the cosmic microwave background, CMB, the faint afterglow of the Big Bang. If a significant fraction of the first generation of stars collapse directly into black holes, it could have influenced the thermal history of the early universe. Some scientists have suggested that future CMB observations could reveal indirect evidence of these events by looking for small-scale fluctuations in the temperature and polarization of the CMB. There's also the possibility that some failed supernovae might produce weak, undetectable explosions instead of completely vanishing. In these cases, the star might eject only a small amount of mass before collapsing, creating a faint, fast-fading supernova that is difficult to observe. These mini-supernovae could be lurking in existing telescope data, waiting to be discovered through careful analysis. Ultimately, the study of failed supernovae is still in its early stages, but it has the potential to reshape our understanding of stellar death, black hole formation, and the evolution of galaxies. With new observational tools, including advanced gravitational wave detectors, neutrino observatories, and next-generation space telescopes, we may soon have the ability to detect these hidden events directly. If failed supernovae are as common as some models suggest, it could mean that a significant fraction of the universe's most massive stars are dying in total silence, collapsing into black holes without releasing a single burst of light. This idea challenges our perception of the cosmos, reminding us that some of the most dramatic events in the universe might be happening right in front of us, hidden from view, waiting to be uncovered. As technology advances, we may one day be able to witness a failed supernova in real time, capturing the moment when a massive star simply disappears into darkness. Until then, astronomers will continue searching the skies for more missing stars, hoping to unravel one of the greatest unsolved mysteries of space. The search for failed supernovae is becoming one of the most intriguing frontiers in astronomy, pushing scientists to rethink how stars die and how black holes form. While the traditional model of stellar death assumes that most massive stars end their lives in explosive supernovae, the possibility that a significant number of them simply collapse into black holes without any visible explosion raises profound questions about the unseen processes shaping our universe. But if these events are so elusive, how do we even begin to detect them? The answer lies in a combination of indirect observations, theoretical models, and cutting-edge technology that allows us to probe the hidden corners of space. One of the key methods astronomers use to identify potential failed supernovae is long-term monitoring of massive stars in nearby galaxies. By carefully observing these stars over time, researchers can look for cases where a massive star suddenly vanishes from view without producing a detectable explosion. This is exactly what happened in the case of N6946bh1, where a bright red supergiant simply disappeared from telescope images. Such events provide some of the strongest evidence that failed supernovae are real, but the challenge is that these vanishings are extremely rare and difficult to confirm. To improve the search, astronomers have turned to some of the most advanced telescopes available, including the Hubble Space Telescope, the Spitzer Space Telescope, and the Very Large Telescope, VLT. These instruments allow scientists to examine the regions where these missing stars once existed, searching for any faint infrared or radio signals that might indicate the presence of a newly formed black hole. While direct evidence is still scarce, some tantalizing clues suggest that these collapses could be more common than we once thought. One of the biggest difficulties in studying failed supernovae is the fact that most of the action happens deep inside the star, hidden from our view. When a star undergoes core collapse, the intense gravitational pressure at its center causes the core to shrink into an incredibly dense object. If the conditions are right, this collapse can trigger a shockwave that rips through the outer layers of the star, producing a bright and violent explosion. But if the collapse is too extreme, the shockwave might fail to escape, and instead of a spectacular explosion, the entire star simply implodes. This process is thought to occur when a star's core reaches a critical mass, exceeding the so-called maximum mass, that can be supported by neutron degeneracy pressure, the force that keeps neutron stars from collapsing into black holes. In such cases, the core collapses directly into a black hole in a fraction of a second, and any outward explosion is suppressed. Without a powerful shockwave to eject the outer layers, the star's material is quickly swallowed by the forming black hole, leaving little or no visible trace of the event. However, while these collapses might be invisible in the traditional sense, they are not necessarily without consequences. One potential way to detect failed supernovae is through their impact on nearby space. When a star collapses into a black hole, it can generate a brief burst of high-energy neutrinos, tiny, nearly massless particles that rarely interact with normal matter. Unlike light, which can be blocked by gas and dust, neutrinos can pass through almost anything, making them a valuable tool for studying hidden astrophysical events. Neutrino observatories like IceCube in Antarctica are designed to detect these elusive particles, and while no definitive neutrino burst from a failed supernova has been observed yet, future detectors could provide new insights into these mysterious collapses. If we could pinpoint a sudden neutrino burst from a region where a massive star was previously visible, it would provide strong evidence that the star had collapsed directly into a black hole without a visible explosion. Another indirect signature of failed supernovae comes from the study of black hole populations. If a large fraction of massive stars undergo failed supernovae instead of successful explosions, it would suggest that black holes form much more frequently than we currently estimate. Recent observations of binary black holes by the LIGO and Virgo gravitational wave detectors have revealed a surprising abundance of black holes in the 30 to 50 solar mass range, which is difficult to explain using traditional supernova models. One possible explanation is that many of these black holes formed through direct collapse, rather than through the conventional supernova pathway. If failed supernovae are responsible for producing a significant fraction of the black holes detected by LIGO, it would suggest that these silent collapses are not just rare cosmic anomalies, but a fundamental part of how black holes are created. The existence of failed supernovae also has major implications for our understanding of supernova explosions in general. For decades, scientists have struggled to fully explain how massive stars explode, and recent computational models suggest that the process is far more complex than we once believed. While some supernovae explode violently, others appear to be right on the edge of failing entirely. This has led to the idea that supernovae might exist on a spectrum, with some stars undergoing complete explosions, others experiencing weak or partial explosions, and some collapsing entirely into black holes. If this is true, it could help explain why we observe such a wide variety of supernova remnants, from bright and energetic explosions to faint and difficult-to-detect events. One of the most intriguing possibilities is that some failed supernovae might produce weak, low-energy explosions that are easily missed by traditional surveys. These fissile supernovae could occur when a star partially ejects its outer layers before collapsing into a black hole, creating a dim and short-lived event that is hard to detect. If these events exist, they might be hiding in existing supernova data, overlooked because they don't fit the standard expectations of what a supernova should look like. Future space telescopes, such as the James Webb Space Telescope, JWST, and the upcoming Extremely Large Telescope, ELT, could help identify these elusive events by providing deeper and more detailed observations of distant galaxies. By looking for faint and unusual supernova remnants, astronomers might be able to uncover a hidden population of weak explosions that bridge the gap between traditional supernovae and full-fledged failed supernovae. Another important question is how failed supernovae influence the overall chemical evolution of galaxies. Since supernovae are responsible for producing and dispersing heavy elements like iron and oxygen, a high rate of failed supernovae could mean that some regions of the universe received much less enrichment from stellar explosions than others. This could have significant consequences for the formation of planets, and even the potential for life to emerge in different parts of the cosmos. If failed supernovae were more common in the early universe, it could mean that the first generations of stars contributed far less to the chemical makeup of galaxies than we currently assume. This could have led to significant variations in the abundance of key elements like carbon and oxygen, shaping the environments where the first planets formed. Some researchers have even speculated that failed supernovae could play a role in the mysterious variations in metallicity seen in different types of galaxies. Despite all these open questions, one thing is clear: failed supernovae represent a major missing piece in our understanding of stellar evolution and black hole formation. If these events are as common as some models predict, they could be shaping the universe in ways we have yet to fully appreciate. By continuing to refine our observations and develop new methods for detecting these hidden collapses, astronomers hope to unlock the secrets of failed supernovae and uncover one of the greatest unsolved mysteries of space. As our technology improves, we may one day be able to watch a failed supernova unfold in real time, capturing the moment when a massive star collapses into darkness. Until then, scientists will keep searching for missing stars, subtle neutrino signals, and hidden gravitational wave events, each one a potential clue in the quest to understand how stars die and how black holes are born. The universe is full of secrets, and failed supernovae may be one of its most profound. The implications of failed supernovae extend far beyond individual stars. They could reshape our understanding of how galaxies evolve and how black holes accumulate over cosmic time. If a significant percentage of massive stars are collapsing into black holes without explosions, then it challenges long-held assumptions about how heavy elements are distributed across space. Supernovae play a crucial role in spreading elements like oxygen, iron, and calcium into the surrounding interstellar medium, enriching future generations of stars and planets. But if many of these stars collapse silently, then entire regions of space may be missing these essential building blocks, altering the chemical evolution of galaxies in ways we have yet to fully grasp. One of the most intriguing consequences of failed supernovae is their potential role in the formation of intermediate mass black holes, IMBHs. While stellar mass black holes, which form from regular supernovae, typically range between 5 to 50 times the mass of the Sun, and supermassive black holes in galactic centers can be millions or even billions of times more massive, IMBHs occupy a mysterious middle ground, with masses between 100 and 100,000 times that of the Sun. These objects have been notoriously difficult to detect, leading to intense speculation about their origins. Some astronomers believe that failed supernovae could be a major contributor to this missing population of IMBHs. If certain massive stars collapse into black holes without losing much of their mass, they could gradually merge with other black holes over time, growing larger and eventually bridging the gap between stellar mass and supermassive black holes. In this scenario, failed supernovae could be responsible for the gradual buildup of black holes in dense stellar environments, such as globular clusters and galactic cores. Furthermore, the possibility that failed supernovae can produce black holes with little or no associated explosion has major implications for gravitational wave astronomy. When two black holes merge, they release powerful ripples in spacetime known as gravitational waves, which can be detected by observatories like LIGO and Virgo. The surprising number of black hole mergers detected so far suggests that black holes form more frequently than expected, possibly through direct collapse scenarios. If failed supernovae are producing black holes at a higher rate than traditional supernova models suggest, then we may need to rethink the population statistics of black holes throughout the universe. The challenge, of course, is detecting these events. Traditional supernova surveys focus on bright, explosive events, making them ill-suited for identifying failed supernovae, which leave behind little to no visible evidence. However, some alternative detection methods may provide new insights. One promising approach involves monitoring red supergiants in real time, searching for stars that suddenly disappear from view without producing an explosion. This requires long-term observational programs that track thousands of massive stars over many years, a daunting but potentially rewarding endeavor. Another strategy involves searching for faint afterglows or weak infrared signals that might indicate the presence of newly formed black holes. While most of the collapsing star's material is expected to be swallowed by the black hole, some residual gas may remain in the surrounding environment, emitting faint radiation that could be detectable with next-generation telescopes. The James Webb Space Telescope, JWST for example, is equipped with infrared capabilities that could help identify these subtle signals, providing a new window into the final moments of massive stars. In addition to direct observations, theoretical simulations play a critical role in our understanding of failed supernovae. Computational models of stellar collapse allow researchers to explore different scenarios and determine the conditions under which a supernova might fail. These models suggest that factors such as stellar mass, rotation rate, magnetic fields, and the presence of a binary companion all influence whether a star explodes or collapses silently. By refining these simulations and comparing them to real-world observations, scientists can develop a clearer picture of how often failed supernovae occur and what their consequences might be. One particularly intriguing question is whether failed supernovae could produce detectable bursts of radiation in the form of long-duration gamma-ray bursts, GRBs. While traditional GRBs are associated with the explosive deaths of massive stars, some researchers have suggested that certain failed supernovae might generate weak or unusual gamma-ray signals that differ from standard GRBs. These dark bursts could be the remnants of massive stars collapsing into black holes without producing a visible explosion, emitting only a brief flash of high-energy radiation before fading into obscurity. If such events exist, they could be hiding in existing gamma-ray burst catalogs, overlooked because they do not fit the typical profile of an explosive supernova. Identifying them would require careful reanalysis of archival data, as well as new observations using high-energy telescopes like NASA's Fermi Gamma-Ray Space Telescope and the upcoming COSI, Compton Spectrometer and Imager, mission. The study of failed supernovae also has implications for understanding the environments around supermassive black holes. Some theories suggest that certain active galactic nuclei, AGN, the highly energetic centers of galaxies powered by accreting black holes, may be fueled in part by failed supernovae. If massive stars and galactic centers frequently collapse into black holes without explosions, they could contribute to the growth of the central black hole over time, feeding its accretion disk and driving powerful jets of radiation. Another exciting possibility is that failed supernovae could be linked to mysterious astrophysical transients known as fast radio bursts, FRBs. These millisecond-long bursts of radio waves have puzzled astronomers since their discovery, with potential explanations ranging from magnet Rs to alien technology. Some researchers have proposed that certain FRBs might be produced when a massive star collapses into a black hole, releasing a sudden burst of energy before disappearing from view. If this hypothesis is correct, then studying FRBs could provide a new way to detect and confirm failed supernovae in distant galaxies. Despite the many unknowns, one thing is clear: failed supernovae represent one of the most compelling unsolved mysteries in astrophysics. If they occur more frequently than we currently estimate, they could fundamentally reshape our understanding of black hole formation, stellar evolution, and the overall life cycle of galaxies. By combining observations from telescopes across the electromagnetic spectrum, gravitational wave detections, and cutting-edge theoretical simulations, scientists are gradually piecing together the puzzle of these hidden stellar deaths. As our observational capabilities continue to improve, we may one day witness a failed supernova in real time, capturing the exact moment when a massive star collapses into darkness. Until then, the search continues, driven by the relentless curiosity of astronomers eager to uncover the secrets of the universe. The discovery of more failed supernovae could rewrite textbooks, challenge long-standing assumptions, and bring us closer to understanding the profound forces that govern the birth and death of stars. The search for failed supernovae is not just a quest to understand an unusual type of stellar collapse. It has profound implications for almost every branch of astrophysics. If these events are as common as some models suggest, they could dramatically reshape our understanding of cosmic evolution, from the life cycles of galaxies to the formation of the first black holes in the early universe. One of the biggest questions surrounding failed supernovae is how often they occur. Current estimates suggest that a significant fraction, possibly up to 30%, of massive stars may end their lives this way. However, because they leave behind so little observable evidence, confirming their true rate remains a daunting challenge. One of the most promising strategies for identifying failed supernovae is the systematic monitoring of massive stars in nearby galaxies. Projects like the Survey for Failed Supernovae have been observing red supergiants for years, searching for stars that vanish without an accompanying explosion. This method has already yielded potential candidates, such as N6946BH1, a star in the galaxy NGC 6946 that appeared to disappear in 2009. Though some residual infrared emission was detected, suggesting the presence of a dust-obscured remnant, no bright supernova was observed, hinting that the star may have collapsed directly into a black hole. The James Webb Space Telescope, JWST, is expected to revolutionize the hunt for failed supernovae. With its unprecedented infrared sensitivity, JWST can peer through cosmic dust and detect the faint afterglow of material falling into a newly formed black hole. This could provide the most compelling evidence yet for failed supernovae by revealing the weak, lingering signatures of stellar collapse that other telescopes might miss. In particular, JWST's ability to observe distant, early universe galaxies could help determine whether failed supernovae played a major role in the rapid growth of black holes in the first billion years after the Big Bang. Another major avenue of research is gravitational wave astronomy. Black hole mergers have been detected in surprising numbers by LIGO and Virgo, suggesting that black holes may form more frequently than traditional supernova models predict. Some of these black holes may be the result of failed supernovae, forming in regions of space where massive stars collapse directly into black holes without expelling their outer layers. Future gravitational wave observatories, such as the Laser Interferometer Space Antenna, LISA, will be capable of detecting lower frequency waves from intermediate mass black holes, potentially providing further evidence that failed supernovae contribute to black hole formation across the universe. Failed supernovae may also have a profound impact on the evolution of galaxies. Supernova explosions play a crucial role in regulating star formation by injecting energy into the surrounding interstellar medium, preventing the collapse of gas clouds and slowing the rate at which new stars form. If a significant number of massive stars fail to explode, then galaxies could evolve very differently than current models predict. Regions of space where failed supernovae are common might see faster black hole growth but slower enrichment of heavy elements, leading to star populations with unusual chemical compositions. This idea is particularly intriguing when applied to the early universe, where the first generations of stars, known as population 3 stars, are thought to have been extremely massive. Some theories suggest that many of these stars may have collapsed directly into black holes without explosions, contributing to the rapid formation of the first supermassive black holes. If failed supernovae were a dominant process in the early universe, they could explain why we see fully formed supermassive black holes at such high redshifts, only a few 100 million years after the Big Bang. Failed supernovae might also be linked to mysterious astrophysical events known as fast blue optical transients, FBOTs. These rare, short-lived flashes of light are much brighter than typical supernovae but fade rapidly over a matter of days. Some researchers speculate that FBOTs could represent a rare type of failed supernova in which a small explosion occurs but most of the star's mass is swallowed by a newly formed black hole. Studying these events in greater detail could help determine whether they are indeed connected to failed supernovae or represent an entirely different class of astrophysical phenomena. Another tantalizing possibility is that failed supernovae could produce exotic compact objects, such as boson stars, or gravastars. These hypothetical objects, which exist only in the realm of theoretical physics, could form when a massive star collapses but does not create a traditional black hole. Instead, it might form a stable, ultra-dense configuration of exotic matter that does not have an event horizon. While no direct evidence for such objects exists, some astrophysicists speculate that certain unexplained gravitational wave signals could hint at their existence. The impact of failed supernovae extends even to planetary systems. In regions where these events occur frequently, the formation of planets may be altered by the lack of heavy elements typically ejected by supernovae. Some planetary systems might form with unusual compositions, lacking key ingredients for life as we know it. Conversely, in certain cases, failed supernovae might create conditions that are more favorable for the formation of massive planets, as the gravitational influence of a nearby collapsed star could shape the distribution of gas and dust in ways that promote planetary growth. Despite the growing body of evidence supporting the existence of failed supernovae, many unanswered questions remain. What determines whether a massive star explodes as a supernova or collapses silently? Are failed supernovae more common in certain types of galaxies? Do they primarily produce black holes, or could they sometimes result in neutron stars or other exotic remnants? These mysteries drive ongoing research, with astronomers using every tool at their disposal to uncover the truth about these hidden cosmic events. Ultimately, the study of failed supernovae is not just about understanding how stars die. It's about uncovering the hidden forces that shape the evolution of the universe itself. If we can determine how frequently these events occur and what kinds of remnants they leave behind, we may unlock new insights into the origins of black holes, the chemical makeup of galaxies, and the fundamental processes that govern the cosmos. The search for failed supernovae is a testament to the ingenuity of modern astronomy, pushing the boundaries of what we can observe and understand about the most extreme events in nature. As telescopes become more powerful, gravitational wave detectors more sensitive, and theoretical models more refined, we may soon uncover definitive proof that failed supernovae are not just a rare anomaly, but a fundamental part of the cosmic life cycle. And when that happens, it could reshape everything we thought we knew about how stars live and die. The universe, as always, is full of surprises, and failed supernovae may be one of its most profound and mysterious secrets. The implications of failed supernovae go beyond just black hole formation and missing explosions. They challenge the very models that astrophysicists have relied on for decades. Traditional supernova theory suggests that massive stars should explode in a predictable way based on their mass, composition, and nuclear processes. However, if a significant number of these stars are instead collapsing directly into black holes, then there are forces at play that scientists don't fully understand yet. This could mean that the equations governing stellar evolution need revision, or that hidden variables, perhaps related to the properties of dark matter, neutrinos, or exotic quantum effects, are influencing the fate of dying stars in unexpected ways. One particularly perplexing question is whether failed supernovae occur in patterns or clusters. If they are randomly distributed, then their influence on galactic evolution might be minimal. But if they tend to happen more often in certain environments, such as in metal-poor galaxies, regions with high magnetic fields, or areas with intense cosmic radiation, then they could be playing a much larger role in shaping the cosmos than currently believed. Some researchers suspect that failed supernovae might be more common in low-metallicity stars, which are abundant in the early universe and in dwarf galaxies. If that's true, then these silent collapses might have been a dominant mechanism for early black hole formation, helping to seed the supermassive black holes that now anchor many galaxies. A major challenge in studying failed supernovae is distinguishing them from other cosmic events. For example, when a massive star collapses into a black hole, it may emit a brief burst of neutrinos, a near undetectable signal that could be our only clue that the event occurred. However, similar neutrino bursts can be produced by other astrophysical phenomena, such as neutron star mergers or gamma-ray bursts, making it difficult to definitively attribute them to a failed supernova. This is where multi-messenger astronomy, the combination of traditional telescopes, gravitational wave detectors, and neutrino observatories, becomes crucial. By combining data from multiple sources, scientists hope to build a clearer picture of how often failed supernovae occur, and what specific signals they produce. Another potential method for detecting failed supernovae involves looking at the motion of companion stars in binary systems. If a star in a binary pair suddenly collapses into a black hole without an explosion, its companion should experience a sudden, unexplained change in velocity. By studying massive star binaries with precise measurements of their orbital motion, astronomers might be able to catch cases where one star simply vanishes, leaving behind an invisible but massive remnant. Some researchers believe that certain runaway stars, stars that appear to be moving through space at high speeds, might have been ejected from binary systems when their companion underwent a failed supernova. Failed supernovae also raise questions about the so-called mass gap in black hole populations. Observations from LIGO and Virgo have shown an apparent shortage of black holes in the range of 2.5 to 5 times the mass of the Sun. One possibility is that failed supernovae produce black holes in a way that naturally avoids this mass range, either because of the physics of direct collapse or due to some hidden effect of neutrino-driven mass loss. If this turns out to be true, it would provide critical insights into both stellar physics and the mechanics of black hole formation. Another intriguing consequence of failed supernovae is their potential role in cosmic structure formation. If enough failed supernovae occur in a particular region of space, they could significantly alter the gravitational landscape, influencing the movement of gas clouds, the formation of new stars, and even the development of large-scale cosmic structures. Some researchers speculate that failed supernovae may contribute to the formation of ultra-compact dwarf galaxies, small, dense galaxies that contain a disproportionate number of massive black holes. If true, this would suggest that these events are not just isolated stellar deaths, but key players in shaping the architecture of the universe itself. There's also the question of how failed supernovae interact with dark matter. While dark matter remains one of the biggest mysteries in physics, some theories suggest that its distribution and behavior could influence how stars die. If dark matter interacts with ordinary matter in subtle ways, it might tip the balance between a successful explosion and a silent collapse. Conversely, if failed supernovae produce gravitational effects that we don't fully understand, they could be contributing to the observed anomalies in dark matter distribution. Some radical hypotheses even propose that failed supernovae could produce dark black holes that form in regions with high concentrations of dark matter and behave differently from those formed in traditional stellar environments. One of the most ambitious goals in astrophysics is to create detailed simulations of failed supernovae that can accurately predict their behavior. Current computational models struggle with the extreme conditions present during stellar collapse, requiring advanced algorithms and massive computing power. However, as supercomputers become more powerful, researchers hope to refine these models and develop simulations that can match real observations. By doing so, they might finally be able to determine why some stars explode while others collapse silently, solving a mystery that has perplexed scientists for decades. Failed supernovae also challenge our understanding of the so-called stellar graveyard. Traditionally, it has been thought that stars end their lives as white dwarfs, neutron stars, or black holes. But if failed supernovae are as common as some models suggest, then there may be other, as yet undiscovered types of stellar remnants lurking in the universe. Could some failed supernovae leave behind exotic objects that defy classification? Could they be responsible for some of the unexplained transient signals detected by telescopes? The possibility that failed supernovae might be producing unknown phenomena adds another layer of intrigue to an already mysterious subject. The ultimate question is, just how common are failed supernovae? If they represent a rare, exotic process, then their impact on cosmic evolution may be limited. But if they occur frequently, potentially accounting for a significant fraction of all massive star deaths, then they could be reshaping galaxies, influencing black hole populations, and even playing a role in the formation of large-scale cosmic structures. As observational techniques improve and theoretical models advance, we may soon have definitive answers. The study of failed supernovae is still in its early stages, but it has the potential to revolutionize our understanding of the universe. From the birth of black holes to the structure of galaxies, these silent collapses could be a missing piece in the cosmic puzzle. And as we continue to explore the mysteries of the cosmos, one thing is clear: the more we learn, the more questions we uncover. The universe is full of hidden phenomena, and failed supernovae may be one of its most profound secrets, waiting in the darkness, just beyond the reach of our current knowledge, ready to change everything we think we know about how stars live and die. The concept of failed supernovae raises fundamental questions about the very nature of stellar evolution. Scientists have long believed that the life cycle of a massive star follows a relatively predictable sequence. Nuclear fusion sustains the star for millions of years. It eventually runs out of fuel, the core collapses, and an explosion ejects the outer layers in a dramatic supernova event. However, the realization that some stars may bypass the explosion altogether and collapse directly into black holes challenges this entire framework. It suggests that the death of a star may not be as simple as mass alone determining the outcome. Instead, there could be a hidden set of physical parameters, perhaps related to rotation, magnetic fields, or interactions with surrounding matter, that dictate whether a star goes out with a bang or simply fades into cosmic oblivion. One of the biggest challenges in detecting failed supernovae is the lack of obvious visual evidence. Traditional supernovae are some of the brightest events in the universe, releasing more energy in a few weeks than our Sun will emit over its entire lifetime. This makes them relatively easy to detect with modern telescopes. Failed supernovae, on the other hand, do not produce a brilliant explosion. Instead, the star simply vanishes from sight, leaving behind little more than a gravitational shadow in the form of a newly formed black hole. The only observable sign might be a brief flash of neutrinos, a nearly undetectable burst of ghostly particles that interact so weakly with matter that they can pass through entire planets without being stopped. One way astronomers have attempted to identify failed supernovae is by conducting long-term monitoring of red supergiants, massive stars that are nearing the end of their life cycles. If a red supergiant disappears without producing a visible explosion, it could be a strong candidate for a failed supernova. One of the most promising examples was identified in 2017, when a team of astronomers studying the galaxy NGC 6946 observed that a massive star, designated N6946 BH1, simply faded away over the course of several years. This was highly unusual. If the star had gone supernova, it should have produced a bright explosion, but no such event was observed. Instead, the star appeared to collapse directly into a black hole, making it one of the best pieces of evidence yet for a failed supernova. Failed supernovae also have significant implications for the study of black holes. If many massive stars collapse directly into black holes without an explosion, then the number of black holes in the universe could be much higher than previously estimated. This could help explain the existence of supermassive black holes, which are found at the centers of galaxies and whose origins remain one of the greatest unsolved mysteries in astrophysics. It is possible that a significant fraction of these behemoths grew from an early population of failed supernovae, slowly accumulating mass over billions of years through mergers and accretion. Another intriguing possibility is that failed supernovae could produce so-called hidden black holes that do not emit detectable X-ray radiation. Most known black holes are identified through their interactions with companion stars, where the black hole pulls in gas from its neighbor and heats it up to millions of degrees, producing bright X-rays. However, if a failed supernova results in a black hole that is not actively accreting matter, it could remain entirely invisible. This raises the possibility that the universe is filled with an unseen population of black holes that have formed through failed supernovae but remain undetectable because they are not currently feeding on surrounding gas. The role of failed supernovae in galactic evolution is another area of active research. Supernova explosions are thought to play a crucial role in distributing heavy elements throughout the cosmos, enriching interstellar gas clouds with the building blocks of planets and life. If a large fraction of massive stars are undergoing failed supernovae instead, then this process might be less efficient than previously believed. This could mean that certain regions of the universe, particularly older galaxies, might be missing some of the elements necessary for the formation of planets and complex chemistry. On the other hand, failed supernovae might still contribute to element distribution in indirect ways, such as through weak outflows of material or through interactions with other astrophysical processes. The idea that a star can simply collapse into darkness without warning also raises profound philosophical and existential questions. Supernovae are among the most spectacular and well-studied phenomena in the cosmos, serving as cosmic beacons that mark the end of a star's life. But if many stars are instead disappearing without a trace, it suggests that the universe contains far more mysteries than we currently understand. It also highlights how much remains unknown about the fundamental physics governing the life and death of stars. One of the most exciting areas of future research is the potential role of gravitational wave detectors in studying failed supernovae. When a massive star collapses directly into a black hole, it is expected to produce a brief but intense burst of gravitational waves, ripples in the fabric of spacetime that can be detected by observatories such as LIGO and Virgo. If scientists can identify a gravitational wave signature that is unique to failed supernovae, it could provide a powerful new way to study these elusive events. This would allow researchers to estimate how often failed supernovae occur and to explore the physics of stellar collapse in unprecedented detail. Another promising approach involves studying the environments around suspected failed supernovae. If a star collapses into a black hole without an explosion, it should leave behind a distinctive imprint on its surroundings. For example, the material that was once part of the star's outer layers might slowly drift away, creating a faint but detectable nebula-like structure. Additionally, if the black hole formed from a failed supernova is rapidly spinning, it could generate relativistic jets, powerful beams of energy that might be observable with radio telescopes. There is also the question of whether failed supernovae might be responsible for some of the most mysterious astrophysical signals ever detected. Fast radio bursts, FRBs, for instance, are brief but incredibly powerful bursts of radio waves that appear to originate from deep space. While their exact cause remains unknown, some researchers have speculated that they could be linked to failed supernovae, possibly as a result of interactions between collapsing stars and surrounding magnetic fields. If this turns out to be true, it could provide a long-sought connection between failed supernovae and one of the most enigmatic signals in the universe. As technology advances, astronomers will continue to refine their techniques for detecting failed supernovae. Future space telescopes, such as the James Webb Space Telescope, JWST, and the upcoming Nancy Grace Roman Space Telescope, will provide unprecedented sensitivity for observing distant stars and their final moments. These instruments may be able to identify failed supernovae by detecting subtle changes in infrared light, or by studying the remnants left behind after a star's disappearance. Ultimately, the study of failed supernovae represents one of the most exciting frontiers in modern astrophysics. These silent cosmic events challenge our understanding of how stars die, how black holes form, and how the universe evolves over time. They remind us that even in a field as well studied as stellar evolution, there are still fundamental mysteries waiting to be solved. As we continue to explore the depths of space, failed supernovae may turn out to be one of the key pieces of the cosmic puzzle, revealing hidden truths about the universe and our place within it. The deeper we dive into the mystery of failed supernovae, the more it becomes clear that these events challenge not only our understanding of stellar deaths but also the broader picture of cosmic evolution. Failed supernovae could hold answers to some of the biggest questions in astrophysics. Questions about the true number of black holes in the universe, the frequency of massive stellar collapses, and even the hidden processes that govern matter and energy in extreme environments. To fully grasp the significance of these events, we must explore both their theoretical foundations and the observational evidence that suggests their existence. One of the most striking aspects of failed supernovae is how they fit into the broader framework of stellar evolution. The fate of a star has long been thought to be determined by its initial mass. Smaller stars, like our Sun, end their lives as white dwarfs, shedding their outer layers to form beautiful planetary nebulae. More massive stars, those above roughly 8 times the Sun's mass, are expected to undergo core collapse and explode as supernovae, leaving behind neutron stars or black holes. But the existence of failed supernovae suggests that this process is not always so clear-cut. Instead of exploding, some massive stars appear to take a more direct route, skipping the bright supernova phase entirely and collapsing straight into black holes. This challenges the long-standing assumption that supernovae are the inevitable fate of all massive stars. It also raises the question, what is the true dividing line between stars that explode and those that collapse silently? The answer likely involves a combination of factors beyond just mass. Some scientists believe that the star's metallicity, the proportion of elements heavier than hydrogen and helium, plays a key role. Stars with higher metallicity tend to have stronger stellar winds, which can strip away their outer layers and reduce their final core mass before collapse. If the core mass is below a certain threshold, the star may still explode. But if it remains too large, direct collapse becomes more likely. Rotation is another factor that could influence whether a star undergoes a failed supernova. Stars that rotate rapidly might generate strong magnetic fields, which can affect the way material is ejected during collapse. If these magnetic fields are weak or misaligned, they might not be able to power a successful explosion, leading to a failed supernova instead. This idea is supported by computer simulations, which suggest that slight differences in rotation rates can have dramatic effects on whether a star explodes or not. The presence of a companion star could also play a role in determining whether a star experiences a failed supernova. Many massive stars exist in binary systems, where 2 stars orbit each other in close proximity. If a massive star is siphoning material from its companion, it could gain extra mass and increase its likelihood of collapsing directly into a black hole. Conversely, if it loses mass to its companion, it might avoid direct collapse and still explode. This means that failed supernovae might be more common in certain types of stellar systems, particularly those where mass transfer has played a significant role in the star's evolution. Observational evidence for failed supernovae is still in its early stages, but one of the strongest clues comes from long-term monitoring of massive stars. As mentioned earlier, the discovery of N6946 provided one of the best candidates for a failed supernova. This star, which was estimated to be about 25 times the mass of the Sun, gradually faded from view without producing an explosion. Before disappearing, it experienced a brief increase in brightness, a possible indicator of a weak failed supernova, where the core collapse was not entirely silent but still failed to produce a full explosion. This observation raises an interesting question. Do all failed supernovae involve some sort of faint transient event before the star disappears? Some researchers believe that even in cases where an explosion fails, the collapsing core might still generate a brief burst of energy, perhaps from the infall of material or the formation of a nascent black hole. These transient flashes might be too faint to detect with most telescopes, but as observational techniques improve, scientists may be able to identify them more reliably. Another potential way to detect failed supernovae is through neutrino observations. During core collapse, a massive amount of energy is released in the form of neutrinos, almost 99% of the total energy output. In a typical supernova, these neutrinos escape and interact with matter in the outer layers of the star, contributing to the explosion. However, in a failed supernova, these neutrinos might be the only signal that the collapse has occurred, since no explosion follows. Large-scale neutrino observatories, such as the Super-Kamiokande detector in Japan and the IceCube Neutrino Observatory in Antarctica, could provide valuable insights into these invisible stellar deaths. If a massive star in our galaxy were to undergo a failed supernova, these detectors might pick up a burst of neutrinos even if no explosion is visible in optical telescopes. By comparing the timing and energy distribution of these neutrino signals, scientists could gain a better understanding of how failed supernovae occur and how often they happen. Another intriguing possibility is that failed supernovae might be connected to some of the most enigmatic phenomena in the universe: long-duration gamma-ray bursts, GRBs. These high-energy bursts are among the most powerful explosions ever detected, releasing more energy in a few seconds than the Sun will emit over billions of years. While many GRBs are thought to originate from collapsing massive stars, some researchers have speculated that a subset of them might be linked to failed supernovae. In certain scenarios, if a failed supernova leads to the formation of a rapidly spinning black hole, the energy from the collapsing material could generate twin jets of relativistic particles, producing a gamma-ray burst. This would mean that failed supernovae are not always completely silent. In some cases, they could actually be responsible for some of the most extreme events in the cosmos. If this theory is correct, it would provide a fascinating new link between failed supernovae, black hole formation, and the high-energy astrophysics of gamma-ray bursts. The implications of failed supernovae extend far beyond individual stars. They could also reshape our understanding of galaxy evolution and the distribution of black holes in the universe. If failed supernovae occur more frequently than previously thought, then black holes may be far more common than astronomers currently estimate. This could explain why many galaxies, including our own Milky Way, seem to contain more black holes than would be expected based on supernova counts alone. Furthermore, if a significant fraction of massive stars collapse directly into black holes without explosions, it could change the way we think about chemical enrichment in galaxies. Supernovae are responsible for dispersing heavy elements, such as carbon, oxygen, and iron, into space, providing the raw materials for new stars and planets. If many stars undergo failed supernovae instead, then the enrichment process might be slower and less efficient than previously assumed. This could have profound consequences for the formation of planetary systems and even the emergence of life in different regions of the universe. As research continues, astronomers are developing new methods to refine the search for failed supernovae. Future telescopes, such as the Vera C. Rubin Observatory, will conduct wide-field surveys of the night sky, allowing scientists to track the long-term behavior of thousands of massive stars. If a star disappears unexpectedly without a corresponding explosion, it could provide strong evidence for a failed supernova. Meanwhile, advancements in gravitational wave astronomy could offer another way to detect these events. If a star collapses into a black hole, the sudden infall of material might produce a distinct gravitational wave signal, one that could be picked up by observatories such as LIGO and Virgo. Ultimately, failed supernovae represent one of the most compelling frontiers in astrophysics. They challenge our assumptions about stellar death, black hole formation, and even the fundamental forces that shape the universe. As new data comes in, we may find that these silent collapses are not as rare as we once thought. In fact, they might be a hidden but crucial part of the cosmic story, one that has been unfolding right in front of us, unseen, for billions of years. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.